Hello, am I audible? Welcome.
Good morning.
Good morning, sir. Good morning, everyone. So we are about to start. A very good morning to everyone assembled here. I'm Sai Shikha Naidu. Welcome you all on the behalf of School of Studies in Physics, Vikram University, Ujjain. In today's international webinar on emerging interfaces of physics and technology, EIPT-2020. As in this pandemic situation where everything is affected and scattered, webinar sessions are become a boon for our education system as well as the research and development. Aim of this 2 days international webinar is to provide a platform to students, scientists, research scholars, technologists, industrialists to exchange their precious idea and to bring together the fruit of recent development in emerging interfaces of physics and technology. Hello, everyone. We will start our session shortly. We are waiting for more participants to join us. Then after that, we will start our session. I want to convey one message to everybody that if after or during the talks, if you are having any questions, any queries, you should post it on the chat box so that I will convey that question to the speaker. So just keep this thing in your mind that if there is any question, you should post in message box, the chat box, which is present right over there, downward. The broadcasting link, the YouTube link is also mailed to each and every participant. So if you are not able to join here or you want other people or other contacts of yours to join in, so please share that YouTube link and try to join with that YouTube link, as well as you can join from here itself. And it is a request with all the participants that during the talk will going on, nobody will on their mic. You should keep your audio and video close so that we'll get good quality, sound quality of the speaker, what a speaker is saying. If you are having any queries, you should post in comment box so that we'll convey or we'll read out that question or speaker. Nobody will speak in between. It is request with everyone, every participant who is present over here. YouTube link of this 2 days international webinar is also provided to every participant. So for the good audio quality, I request all the participants do not on or unmute your mic and video except the speaker who is delivering the talk or conducting the session. Only that person can on the video and audio. Rest of all, you have to off your audio as well as your video for a good network and audio listening. Welcome everyone. Please keep your audio off so that the unnecessary voice will not come on the main mic. Just keep your audio off and video itself. I request all the speakers to keep audio and video right now off. When their turn will come, at that time, they will start their video and audio. Till then, keep your audio and video off. Welcome
Hello.
everyone.
Sai Shikha,
Yes, ma'am.
now you can start.
Okay, ma'am. Okay, ma'am. Before starting, once again, I want to repeat the messages. YouTube link is also provided by the organizer to every participant Gmail or whatever contact you provided us. So try to check that link also and try to share that link as much as possible to the other participants also. And second thing, during the session, please don't start or unmute your audio or video because it will disturb the connectivity and the net. So for better audio, try to mute your mic and as well as your video also. Okay. So now we'll start the session. A very good morning to everyone assembled here. I am Sai Shikha Naidu. Welcome you all on behalf of School of Studies in Physics, Vikram University, Ujjain. In 2 days international webinar on emerging interfaces of physics and technology, EIPT 2020. Am I audible? Hello?
Yes, you are, ma'am. Please
Yes,
continue.
start.
Okay.
Sai Shikha,
Yes, ma'am. Yes,
we
ma'am.
are
Yes,
we are waiting for Shubha Jain, madam.
okay.
Yeah, I was not able to be connected because I was
Okay,
waiting
okay,
for
no,
last
ma'am.
Sorry,
time.
madam, there was certain confusions. We were searching from your name.
Actually, yeah, I have not an email ID. There is no name, so
Yeah,
that's
yeah.
why it comes from my phone.
So,
Okay, shall I
Shikha,
continue, ma'am?
Shikha, you can now start.
Okay,
And
again, I will
one
start from the
announcement I would
starting.
like to have that YouTube link has been shared on the email of each and every participants and all the groups specifically made for EIPT. So please link or that live streaming via YouTube, because a large number of participants may not gather at this platform, Zoom platform. So YouTube link has also been shared. So please try to go in a YouTube link. And in case of any problem, you can contact us on that those groups specifically made for EIPTs. हाँ शिखा, फिर से बोलो अब तुम.
Yes, ma'am. A very good morning to everyone assembled here. I am Sai Shikha Naidu. Welcome you all on behalf of School of Studies in Physics, Vikram University, Ujjain, in 2 days international webinar on emerging interfaces of physics and technology, EIPT 2020. As in this pandemic situation where everything is scattered and affected, webinar sessions have become a boon for our education system as well as research and development. Aim of this 2 days international webinar is to provide a platform to students, scientists, research scholars, technologists, industrialists to exchange their precious idea and to bring together the fruit of recent development in emerging interfaces of physics and technology. I feel privileged that you all are gathered here for the noble cause. Once Louis Pasteur, one of the biologists, says, "Science knows no country because knowledge belongs to humanity and is the torch which illuminates the world." No matter how critical conditions are, like water, knowledge find its path to flow and it will reach to the destination that is our minds. So, after the phenomenal success of EIPT 2019, we are all set for yet another event, that is 2-day international webinar, EIPT 2020. So again, I welcome you all. Today, due to some urgent official work, our Honorable Vice Chancellor of Vikram University, Professor B.K. Sharma sir, is unable to join us. Now, Professor Shubha Jain ma'am is with us to preside the inaugural session. We are privileged to have you, ma'am, and welcome once again in this event. As a chairperson of the event, we have thank you, ma'am. As a chairperson of the event, we have a Professor Sanjay Kumar Ghosh sir, who is a renowned plasma physicist and former Vice Chancellor of Vikram University, Ujjain. A very warm welcome to you, sir. Before the launch, let me acknowledge the presence of some of our eminent guests. I would like to invite Dr. Swati Dubey ma'am, Head of School of Studies in Physics, Vikram University, Ujjain, to formally welcome the gathering. Over to you, ma'am.
very much, Shikha. Sarve bhavantu sukhina, sarve santu niramaya, sarve bhadrani pashyantu, ma kaschit dukbhag bhavet. A very warm good morning to one and all. It's my proud privilege to welcome you all from the Ujjain, the city of Mahakaleshwar, the seat of wisdom graced by sage Sandipani, King Vikramaditya, and great Mahakavi Kalidasa. I welcome Dean, Faculty of Sciences, Vikram University Ujjain, who is presiding this inaugural session of International Webinar on Emerging Interfaces of Physics and Technology 2020, and Professor S.K. Ghosh, former Vice Chancellor of Vikram University, who is a renowned plasma physicist also, and Professor Raju Khanal from Nepal, who is our invited speaker also of today, Professor Rajendra Chajlani, Professor B.D. Srivastava, and Professor P.K. Sharma, Professor P.K. Dubey. And August gathering on the occasion is of this today's webinar. Physics is most fundamental in all, inclusive of the sciences, and has a profound effect on all scientific and technological developments. In fact, physics is the present-day equivalent of what used to be called natural philosophy, from which most of our modern sciences arose. Physics and technology are closely related. It is true that all forms of technologies are nothing but various sections of physical sciences applied as well as exploited at a larger scale. Our society's reliance on technology is a testimony to the fact that physical sciences play a very significant role in our daily lives too. We all understand the importance of science, technology, and innovations in our day-to-day lives and the ways in which they are transforming the world. If this was not clear earlier, it is obvious now in time of the COVID-19 pandemic situations. Science, technology, and innovation, they are indispensable for our response to and recovery from this crisis also. And the equally important is to introspect and collaborate for the better future. We feel that young minds need to be taught and trained in the recent scientific methods so that they become the future scientists, researchers, in order to showcase their scientific bent of mind and provide them an opportunity to meet, to interact the luminaries in the concerned field. We decided to arrange a platform for interactions among scientists, researchers, faculty members, and PG students. I am sure that this webinar will be an occasion of the exchange of scientific ideas among the best and brightest minds of the world. The talks delivered by the experts will create awareness and stimulate our young generations too. So I hereby extend my greetings to all the invited speakers. Professor Arup Niyogi is also here. And I think there are many participants who could not get logged into this. I think they will be coming soon. So I wish you all a very successful webinar. I welcome Professor S.K. Ghosh once again. He has joined some late. So thank you. And now I wish to have an introduction of our Dean Faculty of Sciences, Professor Shubha Jain, who is presiding over this inaugural session of this today's webinar, international webinar. Professor Shubha Jain is presently H.O.D. at School of Studies in Chemistry and Biochemistry. She is Dean Faculty of Sciences. She is member of Executive Council of Vikram University. She is also member of Evaluation and Planning Board. She is member of Academic Council. She is chairman of Board of Studies in Chemistry, and she is member of various other committees of not only Vikram and of other universities also. She has been an active researcher and she guided 32 PhD students and 150 MPhil students. She authored 4 books and around 120 research publications are there in her credit in national and international journals of repute. She is referee in many international journals. She is life member of Indian Science Congress, Indian Chemical Society, and Indian Council of Chemists also. She graced the post of President of Rotary Club, Ujjain. And we are very eager to hear from you, madam, on this occasion. So I request you to give presidential address. Please, ma'am.
Thank you, Swati, for such a nice introduction, which I think I don't deserve so much of praise. But anyway, thank you so much. Professor Ghosh, he has been my ideal. So, Professor Ghosh and Madam Swati, you are working very well under his guidance. So, first of all, I would like to thank the organizers for giving me this opportunity to be here with you and to address this August gathering of eminent scientists and all the fraternity of physicists. So physics and technology, you know, they go hand in hand. Rather, I would say that their relationship is like hand in glove. No technology is possible without the principles of physics. Whether it is the field of medical science, see, we are using the lasers, X-rays, MRIs, they are all based on the principles of physics. In chemistry, we use these spectroscopes. Quantum mechanics we are teaching, and they all derive their origin from physics. In geology, in other life science subjects, microscopes which are being used of such high precision microscopes, they all have their origin from physics. So physics is, we can say that it is embedded, it becomes the basic science for any field of research. So I congratulate the organizers for choosing such an apt topic for organizing this webinar. So and I'm sure all the students and all the fraternity who are working in the field of physics, they will be benefited by this webinar. So it is a very good effort put in by the Department of Physics. And on this occasion, I would like to welcome Dr. Anup Niyogi from Texas, Dr. Raju Khanal from Nepal, Dr. G.R. Sinha from Myanmar, Dr. D.P. Subedi from Nepal, and Dr. Jamil Alvi from Pakistan on my own behalf and on behalf of Vikram University, Ujjain. So it is our pleasure to have such eminent scientists as speakers in this 2 days webinar. So this, once again, I thank the organizers, I thank all of you, and I congratulate Swati and her team, and I hope you will be benefited of this 2 days webinar. Thank you.
Thank you so much, ma'am, for your inspirational presidential address. We all know that planning and organizing such event need a lot of energy and enthusiasm. Our convener, Dr. G. Ahirwar and Dr. N. Yadav, know their jobs very well and are result-oriented. Now it's time to introduce all of you with motive, utility, and possible outcomes of this event. To tell us about the theme of the webinar, hereby I request Dr. Ganpat Ahirwar, sir, convener of the 2-day international webinar EIPT-2020. Over to you, sir.
Good morning, one and all. Honorable Vice Chancellor, Professor V.K. Sharma, Vikram University, Ujjain. Respected President, Dean of Science Faculty, Professor Shura. Respected Professor S.K. Ghosh, Chairperson, former Vice Chancellor, Vikram University. Respected invited speaker, Professor Anup Niyogi, Professor Raju Khanal, Professor M. Jamil, Professor E. Subedi, and Professor G.R. Sinha. Respected Ideator, H.O.D, Dr. Swati Dubey, respected convener Dr. N. Yadav, and all participants. Myself, Dr. Ganpat Ahirwar, convener EIPT 2020. I hereby convey about the theme of this webinar. This international webinar aims to provide a platform to physicists, scientists, researchers, and technologists from different parts of the world to discuss their latest innovative research ideas and most recent technologies and trends in the field of physics. The major focus of the webinar is to promote interaction and exchange of ideas and provide a global forum for discussion. I am very glad to share that EIPT 2020 is fifth event in the EIPT series. School of Studies in Physics organized 3 national and 1 international conferences under the same banner. This is a 2-day event. I am pleased to welcome you all on the first day of this webinar. Professor Anup Neogi and Professor Raju Khandal are our invited speakers today. Tomorrow, Professor Jamil, Professor D. Subedi, and Professor Jiarsana will give their invited talks. During this COVID-19 time, has become an opportunity for all of us that we could be together online. So let us have some benefit of knowledge sharing. Once again, I welcome you all and hand over the mic to Ms. Tanisika. Please.
Thank you so much, sir, for the motivational words. Now, without wasting a single fraction of second, let's start with the invited talk of Day 1 EIPT 2020. I would like to call Dr. Apurva Mule ma'am to introduce our first speaker. Over to you, ma'am.
Bittu.
बंद हो गया
Dr. Apurva Mule ma'am, can you hear me?
Yes, I can hear you. A very good morning to all. Myself, Dr. Apurva Mule. Here I am to introduce Professor Arup Neogi, sir. Professor Neogi is a distinguished professor of physics at the University of North Texas. He is the director of NSF Emerging Frontier Research Initiative Program on the phononic using additive manufacturing. He has been a senior associate of the National Research Council, a Japan Society for Promotion of Sciences, invitational fellow as well as postdoctoral fellow. He has been awarded the NIDO Fellowship, which is an industrial technology fellowship to pursue research activities in the area of femtosecond technology. He has over 250 technical publications, 1 book, and 2 issued patents, and the 2 pending patents. He has received the Indian Science Congress Young Scientist Award in addition to MP Young Scientist Award for his work in India. His expertise is in the area of ultra-fast optical and optical characterization of materials, including nonlinear optical and near-field optical spectroscopy. He has industrial collaboration for developing hybrid materials using additive manufacturing technology for biomedical applications. Now, after his brief introduction, I would like to invite Professor Niyogi sir to present his talk.
Hello, thank you. Thank you very much for the kind introduction. I really appreciate the invitation, and it's been a pleasure to meet you all online, even though I would prefer a personal meeting under better times. But under the circumstances, it's good to be around, even though it's almost midnight here in Texas. It's almost 11:30 at night. I've never given a talk at this hour, but it's an amazing experience to see all of my former teachers, where I spent my doctoral years as a graduate scholar at the university, at Vikram University, and also some of my former colleagues, Dr. Ghosh, my advisor, and my is someone whom I always respect, and is one of my idols in my years of research. So today I'm going to present some. Let me share my screen, and what I'm going to do is I'm going to present some of our recent work. This is something very different from what I probably presented to some of you before. And let me see if I can successfully. Okay. So I am still a semiconductor spectroscopist to a large extent, but today the talk I'm going to present is at the interface of physics and industry to a large extent. And this is something which we have been switched over quite a bit, and I have a fairly large group in this aspect where we simply have moved to the acoustic analog of optics. So in the US, it's usually a funding-driven process where the next generation of science and technology is being sought out by the research community in a way where we tend to look at exactly what's going to be driving force in fundamental science as well as application. So in the last few years, I mean, I would say in the last 10 years or so, I had a more of a minor project in the area of acoustics because simply optics was too expensive. I mean, as it was mentioned in my introduction that I'm still an ultrafast optical spectroscopist, which I learned in Japan. And then basically from there, we moved on to near field optics or nanophotonics, which is still a large part of what we do. But if you look at our recent publications, we have been moving on more towards machine learning and even ultrasonic spectroscopy. So today what I'm going to keep my talk in like for around 45 minutes to 50 minutes. And this is, I would not say very seminal because since I'm trying to present most of our recent advances, I thought I would just briefly introduce the topic of phononic crystals and then go on to the applications. So we are a part of a large group. I have a National Science Foundation project on the Emerging Frontier Research Initiative of NSF, which basically is the next generation of science and technology, which basically comes up which is being chosen by the research community in the US. So our topic was mostly how can we manipulate sound and light waves in a non-reciprocal manner. So I initially didn't want to put in non-reciprocity in there because non-reciprocal sciences is something which is really fundamental, and I was not sure if I had the time to get into that, but I decided since this is a physics community, I rather would present part of the talk about non-reciprocal sciences. So I'll try to keep it simple. I have been with Dr. Ghosh, with Ghosh sir, I have been a theorist in India. My first PhD in physics was in theoretical physics. but I went to Japan, and then I had a second PhD, which was in electrical engineering. So it kind of helped me to learn a bit about working together as an experimentalist. And now I have a team which actually has pretty much everything from experimental to computational to as well as theoretical analysis. So I lead a team where we have two faculty members, my theorist, Arkady Krokin, and my mechanical engineer, Taeul Choi, and Zeke Walker. He was my graduate student and a postdoc, and now he started his own company. So he works with me on developing ultrasonic devices. Then my postdoc, Hyenu, is also a mechanical engineer. And then the rest of them are basically my graduate students. Of these, some of them, most of them, these fellows shown here are working in acoustics. I have a different group in phononics. So this is my group in phononics, where we have like around 6 or 7 students in phononics. The students in Texas, we have a very, very good high school program in our university where we could actually get some of the brightest kids in their high school who works in our lab. This year has been very, very challenging because of COVID. But since we are doing some COVID research, we are also trying to develop a diagnostic tool for COVID diagnostics. So I could keep my lab open despite everything. I mean, my lab was probably one of the 2 or 3 labs in the entire university which we could keep on open under very strict social distancing. But fortunately, we did not shut down, and I could get some work done. So there's a whole bunch of activities we do in our group. I'm going to pick up just 3 topics today. I'm not going to talk about any photonics. I mean, last time when I went to Ujjain, I did talk about our work on nonlinear optics, but I'm not going to get to optics today. Maybe next year, if I get invited, I can talk about that. But there's some of the work where we published in last year. One actually, this Nature Communication Physics just came out. I'm not going to talk about that because this is on hyperbolic acoustic material work, which basically is a very interesting work on how we can use an acoustic superlattice to focus sound beam. Then, of course, like we have a very large project from the state of Texas where we look into additive manufacturing, like in other words, what people call as 3D printing. But we have like a whole bunch of material scientists working on different types of printers. My group is more towards the diagnostic part of it. Can we really look into the quality of the printing? Can we look into the mechanical property of what people make? 3D printers are very popular. You can make anything with that. But the question is, what is the quality of these things, and how can we improve it? What are the basic material physics behind it? How exactly the grain boundaries occur when you're printing metals? When you're trying to make two or three different alloys, then how does the alloy formation work? All those things, we are looking at that. I'm not going to talk about that as well. This is something which we published on ultrafast plasmonics in last year, one of my grad students. And then we have a whole bunch of 3D printers. We are trying to make light-induced 2-photon polymerization printing. Then we are trying to make artificial lungs, which can be used for COVID diagnostics. Can we actually pick up the scar tissues from COVID-19 infection, which can be picked up by ultrasound spectroscopy? So one of the main things that I'm going to talk about is how we can manipulate sound waves. How can we use basic physics? How can we break the laws of physics to manipulate sound waves? So that's basically is the talk that we have, which actually works on. Since it's non-reciprocal, I'm going to talk a little bit of non-reciprocal sciences, but not exactly these things that we are showing here. Can we make an acoustic diode? Can we control sound wave like light wave? It's very difficult to control sound wave because we cannot manipulate sound with magnetic field like we can do with light. Maxwell's equations unfortunately don't work for sound wave propagation. So it makes it tricky for us to manipulate sound waves. So you have to be very innovative to kind of control sound waves, whether we want to make a lens, whether we want to make a filter. It kind of, is somewhat different approach than we normally do. So this at the bottom, there is like, this is a 3D image which shows how we can actually take an ultrasound tomography of a 3D printed structure. So this metal block was printed using a metal 3D printer, and how we can actually, without cutting it, how can we print this entire structure. And then of course this part, I'm going to talk a little bit about this, where we do some bioimaging. There's a recent paper which is still not out, which has got accepted just this week on the biomedical application of ultrasonic imaging. So this is the kind of outline of my talk. I'm going to briefly introduce for the students and those of you who are not familiar or in this field about the concept of wave propagation and phononic crystals. What are phononic crystals? We know how exactly waves propagate in a phononic crystal, and then I'm going to go to the refractive devices based on phononic crystal, because this is something which is not direct. We cannot make a lens the way we do in optics. So how do we play that thing in case of acoustics or ultrasonics? And then of course, like, we have patented this technology where we can use ultrasound to look into these elastic property of material. And that's something which we use for looking into the elastic property or differentiation of tissues and bones. So I'm going to, that a little bit without the, complicated equations that goes into that. And then of course, of how we use bioimaging or these techniques of, say, metamaterials and meta lenses and elastography to actually image a biological sample. And I'm going to talk a little bit of non-reciprocity. One of my graduate students' project is very ambitious. He's trying to make a laser analog of ultrasound, which is probably a little too ambitious, but we are trying that anyways. So what are phononic crystals? Phononic crystals are basically, like nothing but, you can imagine like a simple, whether you consider it one-dimensional, two-dimensional, three-dimensional structure, where you can have alternating medium with different elastic properties. In case of like, light, you can think of these properties being, if you want to make a photonic crystal, this can be simply materials which can have different refractive indices or dielectric constant, or in this case, like if in case of a phononic crystal, basically you can think about different kind of fluids or solid in between, with fluids in between them. You can take this. So this is a one-dimensional grating structure that you can think where the periodicity is in one direction. If you make it like a checkerboard type, then basically it becomes a two-dimensional phononic crystal. Whereas these yellow ones might be the fluid, and this red ones might be the solid object in there. And then of course, if you can make this in 3D with beads and stuff like that, then basically this becomes a 3-dimensional phononic crystal. So this is quite similar to what you have seen in basically in lattice structure in electronics. The only difference between, say, an electronic lattice and a phononic lattice, if you can think about this, is the dimension of the wave that propagates through it. So these basically, like an electronic structure where you have an electronic band gap. For example, if you take an insulator or a semiconductor, you're going to have an electronic band gap where the eigenstates are not allowed through this, or certain frequency are not allowed depending upon the effective mass of the electrons of the holes, or maybe the property of the material itself. So similarly, have the sonic band gaps, as we call as, or something called as the sonic insulators. So like we can do it in kind of case of an electron, you can actually have a defect which can be embedded inside. So in the same thing, we can actually play with the elastic property of these materials. So you can actually create a defect inside it, and you can actually create a defect which can be along the entire length of this structure, which can make it something which we call it like a waveguide structure. So with this, I mean, like, this is something which, even though this started in the 90s, it's still a fairly young field. I mean, like compared to optics, this is relatively still new, I would say. So you can actually make something quite useful with this. I mean, this is something at the University of Manitoba in Canada, where they actually have this phononic structure, which is a piece of art, but it can kind of behave something like a sound barrier of sorts. So, so this is something which crystals can be used to actually even focus the energy into one point. So that's something which I'm going to talk a little bit about today. Exactly how we can use this simple structure, which are very, very easy to make. I mean, you can actually do this in your lab. You can do this in an undergraduate lab. Many of my students are undergraduate students, so they can, or you can use some of these cheap printers to make it. Printers doesn't make your life very easy because the quality of 3D printing is still a lot to be desired, but you can still get these. One of the reasons I started this work was because optics is too expensive, and I had a big group. So I mean, like, some of my students needed to work on something which was not expensive. So we started working on this, and basically now I have more money in this project than my optics project, unfortunately. But still, optics is still very, very expensive. So not that these are cheaper anyways, but at the same time, I mean, like, we can do a whole bunch with this as well. So this is a three-dimensional phononic crystal, which was published by a group in Germany, and this was this was a group which the Spanish group that published this PRL in '98, and these are like one-dimensional structure, which are like grading-like structures. So how does wave propagate through this phononic crystal? For those who are not familiar with this, I have some basic physics 101. So if you take a plane wave, I mean, I'm not necessarily at this point, let's take a light wave, it becomes easy. I'm going to get to the sound part of it. I mean, at this point, consider light wave. It can be, in terms of the electric field, it can be in terms of the magnetic field, or it can be in terms of the vibration, the wave motion itself. If you consider that to be a plane wave, then the plane wave basically goes through. I mean, like, and then if you have a scatter here, the light will be scattered by the scatterer, and you can observe it. So if it's a randomly scattered, I mean, it will be scattered in all different directions. So there is no order to this scattering process. But what happens when you have a periodic scatter? When you have a scatter, like with a, say, for example, a lattice constant of A, in other words, which is repetitive unit cell, then there is something which now changes in this process. So basically, in this case, when the scattering starts, the scattering basically can happen in such a way, and depending on the wavelength of the wave that is propagating through this crystal, most of the waves will propagate through, but there will be some basically which, where this, like, without being scattered, but there will be some of this wave which can be scattered, and the scattering can be canceled coherently. So something which we call as a band gap. And these are two-dimensional structures. These are like rod-like structures that I just showed in the previous plot. So basically, we create a photonic band gap or an electronic band gap depending upon the distance between these scatterers and the wave through which travels through it. So these waves that we have, basically, what are sound waves? Sound waves are nothing but pressure waves. So instead of, like, in the electric field or the magnetic field, we consider a pressure wave here. And the pressure is a function of displacement and time, also forms a plane wave. And this pressure is being transmitted through this medium. Of course, the only thing is, of course, it cannot travel through vacuum. It has to have a medium through it. So like we have in case of a, like a electronic system, or an optical system, you have a block wave where there's a part of the plane wave, and then there you have periodic envelope of this wave, which basically, it repeats itself. So and it has this frequency, which is, has a dispersion because it depends this the wave as it travels through this medium has a certain dispersion. So basically, depending upon the dimensions of this of these scatterers, or the distance between the scatterers, or the lattice parameters, you actually end up forming these dispersion relation, the dispersion curves. In other words, and if you plot the frequency as a function of the wave vector, you actually get the different lattice structure, band structure in there. So these are the so-called band structure, which is for the matter waves or the vibrational sound waves which is propagating. So there can be for certain frequencies, there can be, for certain configurations, you can get a pseudo gap, which is not complete. But like, in certain cases, you actually in certain, positions, certain energy levels, you exactly get a complete gap. So there is, for example, for this frequency, there is a complete band gap, which can be created for this kind of a crystal. So, and in fact, like, this is something which, is an example which was published in PRL by one of my collaborators. We were not at that time working in this area. They basically created a, noise barrier. So basically, if you don't need too many, if you have 3 rows of these steel rods, you can create a very efficient noise, reduction barrier to reduce the actual, intensity of the sound that passes through it, because the audible sound is being blocked off due to these band gaps which are being created because of these phononic crystals in this case. So, so basically, what do we do with this now? I mean, like, one thing is, of course, as I said, you can always make band, these structures which can be, which can form band gaps, but it also can form filters. We can actually have unidirectional proportional sound. I mean, like, I will show you in the last part of the talk how we can use this for, making us like a Caesar, which is an analog of a laser. We haven't made the Caesar yet, but that's some direction which we are working towards. How can we make waveguides? How can we make modulators? And there are also encryption devices, which I can't talk about, but that's something which we're working on as well. So like now, basically, what we are talking about is 2 different things. One is, what I described so far is basically when we have wavelength of the wave, which is compared to the lattice dimensions, which is where we get the phononic crystals or the photonic crystals. What we have a band structure kind of description. But what is acoustic metamaterial? When we look at the frequencies, which are relatively high frequencies, then we cannot describe everything with a band structure description. Then we have to think about the medium as an effective medium description, where the overall dielectric constant is not the dielectric constant, but there's more of an effective dielectric constant, which is being only seen by the wave, which is basically much smaller than the dimension of the lattice itself. So in that case, we can actually have hyperbolic metamaterials. There is a whole bunch of things which people are working on. I mean, our recent Nature paper that came out is basically is based on some of these hyperbolic metamaterials, where they behave as both as a positive and a negative index material at this and then they change if you change the frequency at a certain point. So so these photonic crystals goes through Bragg scattering like you have in electrons, and like you have electron diffraction. So you have light diffraction, sound diffraction, same thing as any Bragg law is being effected. But in the case of acoustic metamaterial, we have a theory which we call as a homogenization theory, where we can work on a certain frequency limit where we can homogenize the system. So these are basically resonance building blocks of like the next generation of artificial materials. So basically what we are saying is this periodic structure, which are already there in, not necessarily present in nature per se, but, we can make these structures and make something very, very useful with this. So, so basically what is this homogenization limit? So when basically have a wavelength, which in this case the wavelength is, the spread is much larger than the wavelength of this lattice constant. In this case, the medium sees that as an effective medium. That's something which we normally see that. But what happens is when we have something which is in this case, like when we are looking at omega tending to 0, we look into the linear domain where the frequency is very low. When the frequency is very low, basically we call this limit as the homogenization limit, where the relationship between omega and k is a linear relationship, and we don't really consider any of these, which is basically not necessarily in this nonlinear regime. So one thing that you'll see is basically when you're looking at photonic crystals, we normally have don't have to worry about the speed of light. But in this case, the speed of sound becomes the most dictating factor. So, the speed of sound can basically change a lot depending upon the filling fraction. In other words, how many what is the density of these rods that basically we are using. So how can we, because that becomes very important, how can we control this refraction of sound? In other words, what is the omega versus k relationship in this case? So the next part that we really have to, people have been looking at is basically how do you use this as a refractive medium? Why is it challenging? So before I go there, what can you do with before I go to the refraction part of it, how do we use this phononic crystals as guiding light or guiding sound? I'm sorry. I keep on talking about light because the light is something which we always use. But how do we guide sound in a certain direction? How can we switch off and off sound like in a certain direction? This is something which we published last year. One of my postdocs from Mexico came and he had been working on this in here. So what we have is, if you take a defect, if you take so in this picture on the right hand side shows a defect, and this defect, basically has a certain mode which can be, created in the forbidden gap. So within the forbidden energy gap, you can create a small, very fine mode which can be created, which is a defect mode as we call it. So if you have a series of these defect mode, you can basically use tunneling. So it is the same thing as quantum tunneling, but this is quantum tunneling in the acoustic domain. So basically the idea is similar, even though we really have not used any quantum theory to actually simulate this. Our simulations are all done in COMSOL, and basically they are all classical. But the mechanism is something similar to that, where basically when you have these defects which are of different shapes and sizes, basically they can support a certain mode through these phononic crystals, which otherwise would be cut off. So what we do is we take a bunch of rods and then we basically replace some of the rods. We create some vacancies around there, and these are like, this entire crystal takes maybe $5 to make. So we can make these hollow rods and defects, and we can have these modes. So in fact, like what I'm trying to say is, without any of these defects, this black line at the bottom is the one where there is no transmission through this phononic crystal. But as soon as I basically have these defects in there, then I start seeing these modes which are now being permitted. So there are certain bands which are being permitted, which we basically picked up because this is a band which we are engineering to try to see whether we can manipulate certain energy levels which basically travels through these bands. So what we did in our experiment was we created these two channels. So this is a very, very engineering project, and if you look into the end goal, but what we started was with very fundamental basic phononic crystal physics that we started with. So we have these two branches of this Mach-Zehnder interferometer as the optics guys use it in telecom, but nobody has done this in case of ultrasonics before us. So we basically use this. In this case, a certain frequency is being transmitted more efficiently through one of the branches, and the other frequency is transmitted through the lower branch. And we basically, everything is being done underwater, by the way. This entire experiment is done underwater. We just use a transducer, which has a large number of frequency band, which eventually is, transmitting all these different frequencies. So what we have is, depending on the intensity of the input source, we can actually change the energy which goes either through this gate or through this gate. So we can basically flip the actual sound coming out, whether from this point of space or this point of space, by just simply increasing the input intensity. So this was the first report on how we can actually it's an entirely linear effect, by the way. So without any nonlinear acoustics, how can we simply use acoustical switching from one point in space to the other point in space? So can we use it for encoding, decoding? I mean, that's something which I will leave it to the electrical engineers. At the same time, I mean, like this part is still under review, where we can actually use this as a waveguide source to transmit. So if you have a sound which comes in, instead of going this way, it can turn this way and go down with a higher intensity. So we can manipulate the direction of the sound. Now coming back to the refractive part of it, how can we make lenses? sonic lenses, you probably have never heard of sonic lens. How can you make, lens, that for sound waves? Why is it challenging? There are two reasons for it. How does optical lenses work? The reason why optical lenses, it's not difficult, is basically we use the refraction of light. So the light velocity is basically lower in solids than in air. So which basically makes the dispersion easier. So you have bending of light, and it focuses down. So if you take a concave or a convex structure, you can tailor it around the dispersion, so that you can focus the light into a point. But it's not so simple in case of sound waves. Two reasons. First thing is basically the sound wave velocity is larger in solids than in air. So if you take a solid structure, you cannot slow the sound down like you do in case of light. Light slows down in solids. And the other thing is sound is also not transparent, in solids. Basically, most of the sound is being absorbed, and basically that really doesn't help. So how do we get around these two fundamental things? We cannot conventionally use classical picture of sound waves and make a sound wave with that. So, but of course, like, if you go to a clinic, is there a question? So if you go to a clinic, I mean, like, how do the ultrasound radiologists, I mean, like, do an ultrasound? They don't really use lenses, by the way, but they can still get the work done. What they do is they basically use a combination of reflecting transducers. So in other words, they simply use mirrors. So you can imagine that they use a combination of mirrors, which basically focuses a certain point, into a focal zone. So all the waves are being reflected off a mirror, and then eventually there are curved elements which are being used to do that. So it's mostly electronics that's being used, and to basically there's focal plane arrays which are being used, phasor transducers. There's a whole bunch of things that are being used to basically focus sound energy or ultrasound energy to a point. So are there any way to do this into, in like an acoustical phononic lenses, which are passive in nature? So the first thing was, being proposed by one of our colleagues in Spain. I mean, like, he's also right now, a collaborator in our project from Santiago's group. They basically used these acoustic metamaterial or phononic crystal lenses to be more clear. So in this case, you can actually create the velocity of this sound wave, which can be less than that of the air within the crystal. So this shows the actual propagation of sound without the lens, like a simple phononic crystal, the same periodicity. But if you actually have this curved structure like a lens, you can focus the sound wave onto a certain point. So so what is the issue with this? There are two things that is an issue. First of all, like in any light based lens as well, photonic lenses as well. If you think of the structure, these are limited by the periodicity of this. Once you fix these rods, the distance and the dimension of these rods and the material of these rods. So if you take steel or aluminum or plastic, you basically pick up your frequency. So what we do is we choose the distance between the rods, or the dimension of the diameter of the rods, or the material property, the elastic property of the rods, to pick up what frequency we want to work on. So the higher the frequency, most of your ultrasound that we use in the clinics are all high frequency ultrasound, 10, 20, 7 to 8 megahertz or so. So they have their own advantages, because the higher the frequency, the better the spatial resolution that we can have. Okay, so if you compare with X-rays, we can never get a resolution with ultrasound which is as good as an X-ray, because X-rays are electromagnetic waves which can give you a very high resolution, because the energy is very small and the wavelength of the light is very, or the X-ray is very small compared to the wavelength of sound. So the sound is a few millimeters in dimension. So the best that you can get is a few millimeters or so. So you cannot get it. So one of the things that my group has been looking at is, can we actually make a lens which we can change the focal length? So if you can change the focal length of the lens without, every time making a new lens, it will make our life much more easier, and then we can basically play with it. So one of the things that we can do is how can we play with the sound wave? So which is something which we started playing with, is like, can I actually make a lens which is tunable? In other words, can we have a focal length which actually can be varied by changing the temperature or by changing something externally, rather than trying to make a new lens itself. So for that, we wanted to make a hybrid lens where we basically wanted to use a polymer. So my group has been working with some kind of polymer which is like polyacrylamide hydrogel. These hydrogels are basically reverse phase transitional polymers. In other words, if you heat it up, it shrinks. So in other words, it becomes dense. As it becomes dense, the density of the medium changes, and as the density of the medium changes, the velocity of the sound changes. So we thought that why shouldn't we use this property where we actually can use this kind of a polymer in the phononic lenses or the phononic crystals to kind of modulate the sound. So one of the first Nature papers that we published from our group was basically how can we use control sound waves with radio waves. So this was the first concept of an active phononic crystal that came up where we control the sound wave using a radio wave. So if you think about it, radio waves are electromagnetic waves, and sound waves are very, very low frequency waves. So they don't even interact. They don't interact with each other. But can we change the density of the medium, and by changing the density of the medium, slow down the speed of sound, and in that way, basically, modulate the sound wave using radio waves? So most polymers are RF, susceptible. So in other words, you can use a radio wave to modulate the density and the temperature of the polymer, because polymers absorb radio frequency waves. So what we did was we basically took a phononic crystal and filled it up with the polymer. This polymer, of course, like we use a whole bunch of different tricks in there. So these polymers actually had nanoparticles which were multiferroic nanoparticles, like barium doped, potassium doped barium titanate kind of nanoparticles, which are very, very highly anisotropic to the radio frequency waves which we used, and basically then created a phononic crystal which we could modulate. So we showed for the first time that we can actually change the transmission bandwidth completely by changing the radio wave. So by just using radio wave, it heats up the polymer and it shrinks the the overall medium and changes the phononic crystal's property, then eventually gives us something which basically is an acoustical modulator which is being controlled by radio waves. We can do this with light, but light is not as effective as radio wave because radio waves can penetrate deep. So this entire thing was being done underwater, as I'm saying, and also in air, because doing underwater was more challenging because the radio waves are being absorbed by the water. So so we use the same things, so we designed a lens which basically can focus this sound waves. So we use the lens which are different kind of acoustical properties we use, and then basically we simulate this lens first, and then we try to see whether this experimentally how close this is to our simulations. And then of course we pick up a frequency at which it doesn't happen at every frequency. So there is only certain frequencies at which you can see this focusing property. So we choose that frequency based on our optimal algorithm search, and it can be something people call it machine learning. We call it just optimization, by the way. So and basically we using a hydrogel, by changing the temperature of the hydrogel, we actually can focus this lens at a variable point. So we can change the focal length just by changing the temperature. So in this case, it's the same lens, but by going from 20 degrees Celsius to 39 degrees Celsius, we can change the focal point from this point to this point. So we can actually get a very, very variable change in temperature range with the position by changing the temperature. So so the way that this, we can next use it basically to see what we can kind of use this as a negative refraction. So what is negative refraction? So normally, if you think about negative refraction, I mean, when you think about it, it goes, instead of going down, it will go in an opposite direction, and then when it comes out, it goes in an opposite. So we have two double negative refraction that happens because of the dispersion relationship of the way that the frequency at which it has an anomalous dispersion within this crystal, and that helps us to get a refraction which is very, highly negative in nature. So we have used that to basically look into some deep tissue imaging. This is something which just got accepted, as I mentioned previously. It's still in press. I mean, hopefully this will be out in a couple of weeks. So this is going to be Nature Communications, where we showed how we can do a deep tissue imaging of soft materials using these meta lenses. So people have been just talking about how to use meta lenses for bioimaging, but our group for the first time actually has shown how we can practically use it. So what we did was a phantom tissue in which we embedded different beads which are of different dimensions, and as you can see that conventionally the red figure really cannot exactly pick up, but the black one, which is the meta lens one, exactly picks up detects these pieces which is inside this tissue. So we have different biological material. In this case, we took carrots and celeries and then some seeds and some cherry inside this gelatin, and basically these are the density of these tissues are more close to our human tissues, so that we can pick up something. So we could pick up this with a much higher resolution than normal transducer can. We can even get to the super resolution limit. So if the biggest problem of ultrasound imaging is it cannot differentiate between two neighboring masses. So if you have two different closed masses, I mean, can we really differentiate that? I mean, so it's really, really hard, but we were surprised. We didn't expect that our lens actually could pick up a very, very small difference between these two objects like that. So and it's not just soft tissues. We showed that if you print out hard tissue, we can even pick up bones in there. So but then again, this is something which was good, but this really did not give us the contrast that we really wanted. So one of the things that one of my student has been looking at is something like how can we look at the mechanical property of this material. So go to modern ultrasound technicians, there is a new technique which is coming up, which is called elastography. So what is elastography? Basically, they look into elastic property of tissues and bones and differentiate things like that. So what they do is they take a probe, and then they send an ultrasound and then get a reflected wave back, and then you pick up the actual change in the modulus of the material. So from that you can pick up some of these effects, and then you have to apply an external stress. A vibration is needed. So all these, there are different types of elastography: 1D, 2D, shear wave, and then stress elastography. So there are a whole bunch of different kind of medical ultrasound which people use. But what we have invented last year, which is submitted for provisional for patent, is basically we use a non-contact mode where we really don't have to touch anything. So we use an ultrasound probe, and then we basically, by using an algorithm, we basically pick up the response of the medium and any change in the actual acoustical impedance due to the change in the elastic constant within the medium. So if there's a material 1, material 2, we can pick up any change in the elastic property due to the difference in the elastic property of these two materials, which will give us an idea of exactly how things are inside, even without touching anything. So we published this in IEEE Ultrasonics last year, where we showed how we can actually pick up, differentiate, say, two polymers or two tissues which are very close, or even solid steel and aluminum which are very close. So so this is like, we are using this kind of a thing for a whole bunch of things. We are, I work as the funding comes in, we are working with a whole bunch of material scientists, metallurgists, to look into aircraft. So basically, one of the biggest problem of the aircrafts are how can you find fault in between two dissimilar metals. So if you have brass and aluminum, can you really pick up a defect in between? So we use this kind of a technique for looking into the joints of dissimilar metals. Then, as I said, we actually also look into steel or titanium, which are like aircraft materials to see whether we can pick up any defect which is being printed by 3D printers, which, as you can see, the blue has a very low elastic property and the red one has a very high elastic property. So the difference between these maybe 5–10%, but we can pick this up even without cutting it up. So without any actual contact, without any destructive testing, this is the first time one can pick up some of these things. We can do shear wave elastography from there. So we are also working on biotissues, which I'm not going to get into, where we are working with a clinical group, trying to see whether we can pick up any changes in the actual bone density for osteoporosis and things like that. So what I'm going to just show is basically one of our unpublished work, which we are writing up to show whether if we can combine the meta lenses with elastography, we can pick up information with a much better resolution. So this is so we are working on with some developmental biologists in this one, where this is an alligator. These alligators actually have scales on the top, and so these are calcified scales. So the age of an alligator basically can be predicted by the density of the scales, or how dense the scales are. So the calcification of the scales basically tells us how old an alligator is. So this is kind of a developmental feature which they use. So we are looking at it from a medical perspective. I don't want to get into that, but our main idea was they came to us and asked us whether we can differentiate between the bone and the tissues around it. So if you look at the X-ray, so this is an X-ray image. The X-ray image doesn't really tell us anything, just was the bone. So it's the bone, but we don't know how much of it is the bone and how much around it is the soft tissue around it. So so we use this combination of so this is the meta lens and this is the elastography. So as you can see, the meta lens gives us a, okay, this is the bone you have, and we can't tell much around it. The elastography gives us the details, which is an actual effective elastography that we can pick up, but it doesn't give us the resolution that we want. So what we did was we basically combined these two techniques, and then we can actually get information which even X-ray cannot tell us. So we can get to this is by the way a 15 millimeter, which is much shorter than the actual wavelength of sound in this case. So we can break the diffraction limit of sound and basically pick up the feature size using ultrasound elastography and ultrasound meta lens combination imaging to basically get a quality of an image which is comparable or better than basically an X-ray imaging that one can get. So so this is something which is I hope can be taken up to the next level with the proper people. So I mean, one of the things that we would like to work in India is perhaps trying to see whether we can this is something which can be commercialized and basically low cost ultrasound system which can be developed and and can be portable and can be used very effectively. So we have a whole other thing that we are trying to image through bones, because as you can see, ultrasound doesn't penetrate bones like X-rays does to some extent. So can we use complementary metamaterials to penetrate bone? That's something which we are competing with the guys in Georgia Tech to see whether we can get that. So I have another 15 minutes or so. So I just want to wrap it up with the last part of my talk, which is basically the biggest source of funding for our project, which is non-reciprocal phononics. So this is something which is very, very hot topic around the world. That we have at least 15 groups in the US, or maybe even more than that, working on non-reciprocal electronics, non-reciprocal phononics, and non-reciprocal photonics. So what is non-reciprocity? This is something which basically can be, understood very simply. So if there are 2 points here, if you have, so what, if you have a source here, and if you have a detector here, and if you have an object in medium in there, okay. So if you change the position and the source and the detector, then if the system is reciprocal, then it doesn't matter. If you change from A, take the A from here to and replace it with the source here. I mean, so basically, if his system is reciprocal, there should be no difference whether you're sitting here and the other person is sitting here, or if you change seats, you can hear the same thing. So in other words, if A can hear B, then B can hear A, and nothing changes. Okay, so that's usually the reciprocity theorem. So in other words, if you have a function like which is, so as a function of position, nothing should change. So reciprocity, but can be a tricky thing basically. So if you have a non-reciprocal system, then how can you make the system non-reciprocal? So in other words, the wave propagates in one direction, but when you look at it from the other side, it doesn't behave the same way. So in other words, can you actually design a system which is basically is unidirectional in nature? So in other words, it is non-reciprocal in nature. So for that, there are a few conditions one need to do. You can basically have an active system. So in other words, you have to break the time symmetry. So if you break the time symmetry, so if you have an active, so this is something which was published by a group in UT Austin, where in Science actually. So they basically showed the first non-reciprocal acoustical system where they have a active medium where the system is moving, and so they break the time symmetry in there, and so you actually get a cavity which basically gives rise to non-reciprocity in nature. So if you look into these three branches, if you have switch between 1 and 2 between the source and detector, you will have a different propagation depending on the propagation of these sound waves. If it is clockwise versus counterclockwise, you will see a very different flow of energy that comes out. The other way is basically if you have a nonlinearity in the medium. So the nonlinearity in the medium can induce a response which can basically breaks the reciprocity of the system. So, so this is something which is conventional. Either you have active linear reciprocal system which breaks the time symmetry and then you get a non-reciprocity, or you basically go and try to create a non-linear medium which basically breaks your reciprocity. So what our group has been doing is, we came across this result pretty accidentally, and that's why probably we got funded by NSF. This is a very competitive, field. So we were nowhere near the big groups. But then we got this result, which basically funding. So what we are the first group that came up with the idea for passive linear non-reciprocal device. And that's something which I'm going to talk about a little bit about it. So before going to that, let's go back to some basic physics. So if you have studied Landau-Lifshitz, one other thing is basically, this there's a reciprocity principle in there. So it says that the pressure at B due to a source at A is equal to the pressure at A due to a similar source at B. So that's what I was saying. If you can hear me, I can hear you. So that's the kind of thing which basically the reciprocity theorem says that. So what happens in a T-symmetric wave equation? So basically you can take Euler's equation. So this is a Euler's equation basically, but then, if you have a complex elastic modulus in there, which is having both the real and imaginary part, you still don't break T-symmetry, and still it is reciprocal in nature basically. So, so the T-symmetric equation is reciprocal in nature. So, but what happens, what you do even, what happens if you include a dissipation in there? So if there's a power dissipation due to viscosity which comes in there. So, and if you have a scatter which is symmetric in nature, then even if you change the source and the drain, you're still gonna get our irreversible nature, which is because of the scattering, but eventually the system will still be reciprocal. So what happens if you look into the instance of Euler's equation, you basically take the linearized Navier-Stokes equation. So the Navier-Stokes equation that we have basically is also, it doesn't have any time reversal embedded in it. But I mean, like, if you take into account the viscosity of the medium, the viscosity which has a gradient of the velocity, this has a term in there which basically can be non-reciprocal if there is no P parity and the time symmetry. So in other words, you have to break both the parity and the time symmetry. So how do you do that? What we did was basically, instead of taking a rod which was cylindrical, we took a rod which basically was asymmetrical in nature. So this is a phononic crystal that I was showing previously, but in this case of the phononic crystal, the cross section of the scatterer is different as the wave propagates from down to up or up to down. So this thing that we have here here basically now actually this is an aluminum rod that we place in water, and basically have the transducers which goes from this side, and then we measure on this side, and so we collect this energy on this side. And so when we look into this, this is a band gap, and where this is a transmission property. So we measure the transmission of the wave through this. So what happens is we can see that at a certain frequency, this can be very, very different. So the transmission of the wave is very different if you go from, you know, the blue, between the blue and the red. So so this shows that this is a non-reciprocal system, which basically is passive in nature. So we published this results in PRL in 2018. If you are interested, you can go and explore this a little more. So the biggest but this is a very tricky thing, because we are basically kind of denying 200 years of physics. We are saying that, okay, even if you have a passive system, you are basically having non-reciprocal in nature. So this led to a whole bunch of controversy which people are still talking about. So we are still trying to fight many of these naysayers, because they say that, okay, if you're trying to disprove 20 years of physics, then you really have to come with the right reason for doing that. Our computational I showed here was all computational. There's really still no theory in this. So if somebody comes up with a fundamental theory, that will be a PRL or nature as well. So what again, so far we have done is we basically we showed that this non-reciprocity that comes in is basically not because of non-reciprocity in pressure, which is very low. If you look into this, non-reciprocity in pressure is very low. The viscosity of water is 1-ish. It's not even in this range. But the viscosity, non-reciprocity in the velocity, because of the gradient of the velocity term that gets into the Navier-Stokes equation, that becomes quite a bit. So that is what leads to this change in the P symmetry and the T symmetry in the medium that we see. So we just have communicated this work. So instead of having a symmetric thing, we actually took a circular system where we have scatters which are of different shapes and sizes, and then we basically show that we can still get the non-reciprocity. So what is the use of this non-reciprocity? Of course, we are getting a unidirectional flow of energy. So what one of my students is trying to do right now is basically, can we trap this energy? Can we trap this energy into a cavity and make something like a laser cavity of some sort? So this is something which is not simple. So for that, we have a whole bunch of these structures we created. We created a cavity of different shapes and sizes. So the cavity that we have is designed to trap a certain eigenmode of the frequency in there, and basically we can try to see whether we can trap the energy which is coming in one direction. And so that wave comes in from one direction and it gets trapped in here. So this is all underwater, by the way, again, as I said. So there's aluminum rods in there, and we basically probe the energy inside this inside the cavity, and then pick up the energy which is being trapped. So if all the rods are facing in one direction, the energy will basically simply flow away. But if this is in the opposite direction, then obviously then the wave will be reflected back, and then it will be trapped in this direction. So this is what we are trying to see, whether we can actually trap the energy in the system. So of course, there's a whole bunch of simulations that needs to go into that to pick up the right mode, because which mode is being trapped is the biggest question. So without getting into too much details of the transmission spectrum, I'm just going to show you the pressure map, which kind of gives us this direction. So what we can see is, in this case, when we have the right condition, we can trap the energy in this cavity, which is higher than that on the outside. So this kind of tells us this is a first step where we have shown that using non-reciprocal passive structures, we can actually trap the energy within this cavity, which can be now be amplified. So we are working on the amplification of this energy to create the next step of a laser, or a Sazer as we call it. So so I think I should conclude by saying that we basically have demonstrated tunable phononic crystal. We use radio waves, we use temperature within a polymer embedded phononic crystal to show the filtering of the sound waves, as well as the modulation of the sound wave. So we create non-reciprocal system to develop the first step for a laser system. And then of course we have these meta lenses, which we have used to to focus sound waves, tunable sound waves, as for additive manufacturing, as well as for biomedical imaging. Okay, so I think phononic crystals are quite interesting things. I mean, fundamentally from both physics point of view, as well as from from an application point of view, as a mechanical engineering I never thought I will work so closely with the mechanical engineers. There's a whole bunch of things I could not talk about where we are trying to do wave function engineering by changing the contour, size, and shape of these phononic crystals by mechanically controlling these unit cells. So that's something which we already have done a whole bunch of work with my group in China. But I think I will stop now and take any questions that you might have, and please feel free to contact me for anything. I guess if there are students, if you are interested, please contact me. You need a GRE, but we have openings in our group for deserving candidates all the time. So I know things are challenging, but at the same time, if you are a student who would like to work and you think you are interested enough, please contact us. Okay. All right. So thank you very much for your attention, and I will take any questions that you might have.
Thank you so much, sir. Now we'll take questions from the audience who are connected through Zoom and YouTube. So very first question is from the Zoom itself. What is the physical mechanism of photonic crystal in animal reflectors?
Okay, so well, if you look into the photonic crystals, hold on, let me get back to this one. Yeah, so so the thing is, if you look into this, there are, yeah, so let me get to this band gap. Okay, so if you take it, whether it is sound or light, it doesn't really matter. So there are certain bands where which are completely forbidden. Okay, so this is the forbidden band. This is the energy level at which the wave cannot penetrate this periodic structure. So this will be reflected back. So for example, if you take butterfly wings, okay, so the butterfly wings, the pigment, that the colors that you see are really not just pigmentation, but these are ideally photonic crystals. So these are photonic crystal reflectors which are on the wings of a butterfly. So whether you see a monarch butterfly or any other blue or the color, so it's basically the blue color which cannot, from the sunlight which falls on, is reflected back to the observer so that you can see the blue color and it doesn't go through. The rest of the colors go through, only the blue is reflected back. That's why you can see the photonic crystal like structure on butterfly like structure which is reflected back. So same thing happens in the sound as well.
Thank you so much, sir. And the previous question was asked by Dr. Ram Prasad Prajapati ji, and sir, hope you'll get your reply. Your query is solved now. And the next question is, could it be used for real-time imaging of treatment of cancer patients by radiation therapy?
Well, I think it depends on the use. Okay, so basically, if you talk about ultrasound focusing, yes, the energy can be focused. So cancer patients, I am not sure of that yet. We have ideas to look into that, but one of the thing that people are looking at is can you penetrate bones? If you can penetrate skulls and bones, then you probably can use it for brain cancer. Okay, so there are a whole bunch of ultrasonic surgery that can be done non-invasively, which one can do very effectively if we can focus the ultrasound with a very high precision. So there's a group in Nottingham, as far as I know, they basically use ultrasound surgery for removing plaques in the heart. So when there is a deposition in the heart because of plaque formation, then instead of doing an open heart surgery, they basically use an ultrasound to knock this off. So ultrasonic surgery is already being done in the US and in the UK, as far as I know. That's an entirely different field of high frequency, high intensity focused ultrasound community in the medical community. But for cancer research, I'm not sure if we are at that point where we can do that. It can be used for diagnostics, say for example, like for mammograms. Mammograms are right now being done with an X-ray. So if you can actually get an X-ray resolution with the way that we are using meta lenses, so I can see that for diagnostics, yes. for cancer diagnostics, I believe that it can be applicable very easily. Yes.
Thank you, sir. This previous question was asked by our YouTuber audience. And now the third question is, how do we measure pseudo gaps?
Oh, the pseudo gaps. Okay. So basically what we can do is we do a transmission measurement. So basically you take the crystal here. Let me show you the setup. Let's see if I have it. So basically, if this is a setup you can see here. So so in this case, this is the phononic crystal, and this is one is a source and the other is a detector. Okay, so the good part about phononics is you can use the same transducer, even though we can use different kind of detectors, but in this case we use the same kind of detector, so that the transducer can also detect and as well as send a signal to basically excite and uncover the entire spectrum. So once we do that, so basically what we can see here is a transmission spectrum. So what is the total, how does the spectrum change? So as you can see that, that this is in decibels, by the way. So if you didn't notice it, so this is a frequency and this is in decibel. And in other words, this is all in log scale. So there's this dips that you can see. This is an, basically more than few orders of magnitude difference in the signal that you can see. So these drops that you can see basically gives us an idea of the pseudo gaps. So if it was a complete gap, you would have seen no signal here. Okay, the transmission will be completely zero. So since there are partial transmission that coming here, so this is probably telling us that we do have partial gap in this, or pseudo gaps as you can call it.
That's all about the question, sir. Thank you so much for explaining phononics, sonic lenses, ultrasonic elastography, and so many other topics so nicely and so precisely. I'm confident that those who are new, for those whom this topic is new, they also are able to connect with this presentation. So I again thank to Professor Roop Niyogi sir for delivering such a nice lecture, and thank you so much, sir.
Thank you very much. Thank you everyone for being here in the talk, and I appreciate the invitation all over again. Thank you very much.
Sir, thank you very much for sparing time from your busy schedule.
Oh no, not at all, not at all. Thank you.
Thank you.
Feedback link is already shared in the chat box. Kindly fill it and then post it. Thank you. Now, after such a nice and informative talk by Arup Yogi sir, now it's time to switch on another talk. Shall we proceed, ma'am?
Yes, proceed.
Yes, please.
Yeah. So now, for introduction of our another speaker, second speaker of day one, Professor Raju Khanal sir from Nepal. I would like to invite Mr. Subhash Chauhan. Sir, over to you.
Am I audible to you, Saishika?
Yeah, sir. You are audible and you are visible too. Thank you.
Thank you very much. It's a great opportunity for me to introduce one of the renowned plasma scientists and physicists of our neighbor country, Nepal. Professor Raju Khanal sir is currently working as professor in physics at Central Department of Physics, Tribhuvan University, Kathmandu, Nepal. He is renowned plasma physicist and academician in Nepal. His research interests are kinetic trajectory, simulation of magnetized plasma sheets, plasma wall transition problem using MATLAB, experiments on arc plasma, radiological mapping in situ gamma ray spectroscopy. He has completed MSc in Physics in 1994 from Central Department of Physics, Tribhuvan University, and title of dissertation was Plasma Wakefield Accelerator and its Transfer Ratio. He has completed his PhD in plasma physics from Institute for Theoretical Physics, Innsbruck University, Austria. His PhD research title was A Kinetic Trajectory Simulation Model for Bounded Plasma. He has more than 26 years of teaching and research experience. He has successfully supervised 5 PhDs and 68 MSc dissertations. And Professor Khanal has published more than 51 research papers in various national and international reputed journals. Apart from all these, we, the member of SS in Physics, always feel connected and attached to the team of team and researcher of Nepal group, Professor Khanal, Professor Subedi, Dr. Roshan sir, and their group members for their humble and friendly behaviors and attitude. We can say these all on our experience, based on our experience with all of you, sir, in EIPT 2015. I think you have remembered our holy celebration with SS in Physics members. We are eager to listen you, sir. Can you hear me, sir?
Thank you. Yes, I can hear you. Thank you
yes,
so
sir.
much.
Now mic is over to you, sir. We are very eager to listen you, sir.
Thank you. Namaste, and it's for this wonderful introduction. I forgot I should have recorded this and shown to my family members whenever, most of the time when they get, angry of me. Anyway, thank you once again for this nice introduction. And above all, I would like to thank Dr. Swati Madam for inviting me. And as you said, I have very wonderful experience. I mean, in Ujjain, in a couple of times that I was there in EIPT and the other one in the engineering conference. So I would like to first bow myself to Professor R.K. Chhajlani, who is not only a great physicist in your place, but also a great human being. I'm a little late, but I want to wish him birthday. Happy birthday, sir. And I remember how you treated me, even though we are very young. And also my very good friend Prerna, who motivated me first time to go to Ujjain. Thank you so much. Now I start with my screen. I want to share. So I'm really honored that you have invited me for this EIPT, of which I have very good memories. And in this situation, of course, even in this situation when we are facing lockdown at homes and we are, I think I'm following the news of India, but we are more suffering from this COVID-19 because of your medical facilities that we have in our country, but still we have to fight this. There is no way. So in this situation, I wish everyone is safe. And now let me start. Okay, I'm sorry, I pressed something quickly. You see, this is in the background is our department, our university, which I could not visit for last couple of months, but we are doing everything online. So today I will be talking about the kinetic trajectory simulation model that we have developed and that we are using to study various bounded plasma of interest. We can do it also for diodes. We can do it for any situation. Of course, we have to be able to model it according to the device. But because I thought it would be, for the title of EIPT, it would be better if I can present some of the results, mostly done by my PhD student and of course associated MSc students, regarding how we use this code to at least understand a little part of magnetic fusion devices. And we want to understand what should be the property of the material at the wall, depending on the theoretical calculation or the simulation that we are doing here. So before I start, let me again say I'm thankful to my professors. Of course, the top one is my professor in Austria, who introduced me to this simulation concept, who was my PhD supervisor, and my my professor in Kathmandu who introduced me to plasma physics, and then many students, mostly master's students, and some of them are PhD students. And recently you heard the name of Roshan Chalise, and many of our students and our group member were there in Ujjain, and they had very good memories. Although we were there in the time of this currency changing, and we had problem with the money, but still we had good memories. And also I have good collaboration with other people in India as well. And I am listing here those who have somehow helped us or collaborated with us in the work that I'm presenting today. So with this, for those who want to know where I am now, in fact, we are very close to you. You know, some part of India is even farther from Ujjain. I'm not sure exactly in this picture, but somewhere here you are, I'm here. And I tried to calculate, I did it also last time, how far it takes to go to Mahakaleshwar from Pashupatinath. It is just, you know, if I can walk without stopping, these days when the flights are suspended, maybe in 10 days or 20 days, I'll be there. And just like you mentioned earlier, and this is a proof that I was in Ujjain in 2015 in EIPC, and also in 16 in a different conference. And I have the memory of, because they announced the one who, while reading my CV, you said, I have one of the best holy memory of my life that was in Ujjain. And not only in the Mahakaleshwar temple where I had in fact, that year I enjoyed two Holi, one here and one in Ujjain. That was completely different in front of Mahakaleshwar Mandir. And my mother was more happy because she don't like me going for conference, but that time she said, you can go anytime you like, please go as much as possible to Ujjain. And then also with the students and colleagues there in the university. And one thing I want to, every time I try to connect, when I hear of Ujjain, we remember this one. In Nepal, we still use the Vikram Sambat. Obviously, in our calendar, as you can see in this picture, is today is not 7th. If you say without saying anything, we will meet on 7th, then I will think you are meeting in Ossos, by a few days more to come. But today is 22nd, and we still use this. And this is not only official, but you know, we get salary according to this calendar. So we don't want to forget this one. And this is, of course, after the name, we have the same name with the Vikram University. And another thing I remember in Madhya Pradesh is, this is a temple in Nepal. This is the place where Sita Mata was supposed to, she was born, and this is the temple where Modi ji was visiting few years, not many years back, just before in early 19, I guess. I'm not sure of this picture, I'm sorry. And here you see Modi ji standing. And if you look, not as an expert, but as a layman like me, if you look, if you are from Tikamgarh area, it looks like the college you have there, the government PG college. And for your information, this temple was built by, I don't remember the name, but it was more than 100 years ago by one of the Maharani from Tikamgarh. And she spent a huge amount of 9 lakh rupees. And we also call this is a 9 lakha mandir. Of that time, of course. So this way, we are very closely connected to MP, Ujjain, and Vikram Sambat, everything. So it's always a pleasure for me. I believe that what I have done in my university is mostly academic work, and because of my student, I could do something, few papers or few results, but still it's an honor when you invite for me like this. And when I looked into the university history, it looks like we are again very close to each other. Like Vikram University was a couple of years elder to us, so you should be leading us. And we were established not very long, about 60 years, and we have more than 50 years of physics courses started. And in the beginning, in fact, our physics courses were started in the university, but they were regulated, or we were affiliated to Indian universities in Kolkata and in Patna. So not only from the time of God Ram, but right now we are always connected. So we are just divided by the political boundary, and this is very honor for me every time to talk or even travel whenever that would be possible. Now in our group, what we basically do is we focus in few areas. And today I'll be talking about the kinetic trajectory simulation model that we have developed ourselves. This is a very simple and very low economically, I mean computationally very low, how you say, demanding code, and that can be used for modeling various situations of interest. And because this is a kinetic code, we can expect immediately that it can provide better insight. Of course, once we can clearly model what we want to study compared to fluid and other codes. So today I'll be discussing about this one, but we focus mainly in plasma activities. So we also do fluid analysis of many plasma phenomena. Mostly we focus on the C3s, and I will come to that point very soon. And we also use peak codes, write ourselves, or use mostly the peak code that have been standardly developed. And after collaboration, I mean coming in contact with Professor Lee, who has developed a so-called numerical experiments using Lee model code for plasma focused devices, which is a tabletop device for fusion, but not for energy purposes, but it can be used for X-ray generation or neutron generation and other purposes or material studies. And we do some numerical experiments. This is not experiment. This is again something like simulation. And because we wanted to develop as a group, so we also started recently arc plasma discharge. And we have been working also in this one, but you know, the experimental facilities in our place is still in the very primitive stage, and we are trying to working hard to get some funding so that we can move ahead with mostly with atmospheric pressure plasma. And of course, if time permits, I will show at least one slide each of some of these activities that we are doing, so that it will be easier for me to get some contact from your side or from the students as well. And also, in addition to that, because of interest in nuclear physics, we have, and one of my students is working in radiological mapping using gamma ray spectrometry, and we are also trying to develop a nuclear capacity, mainly for you know, training teachers and also for some survey type of stops. Now let me go back to the summary of my talk. What I will be doing today, this is not, I mean, just introductory summary, is that in all plasma applications, whenever we try to understand the plasma properties, or whenever we try to use plasma, we know that that has to be confined by the walls. And whenever plasma comes into contact with a material wall, in order to be stable, a sheath has to be formed. So the sheath, in fact, is very, very thin layer, which is of the order of just few dBi length. Compared to the total plasma, it is just, you know, sometimes people even ignore it when they are using it fluid approach. So we are interested in this reason. And the reason why we are interested here is obvious, because it is the layer which separates plasma from the wall. And we want to understand exactly what happens at the wall by the plasma that is coming from the core side. And the other reason is because sheath is very small, we don't need much computational power. And unfortunately, we don't have a supercomputer. We just have a very powerful desktop computer with, of course, advanced core, but not a supercomputer. So it would be easy for us to simulate sheath. In the extreme case, even when we have collision and other multi-component plasma, it will take not more than a few hours, or within a day, we can get some results. And the model which we are using, and I will be discussing today, is the kinetic model that we have developed. And what we are doing in recent time is we want to understand the real phenomena that can be modeled or simulated in the sheath region, and that relevant to magnetic fusion devices. Okay, and as I said earlier, this could be a good tool to understand better. So with my experience from last time, there were many young students and from different fields. So I thought I will give some basic idea about magnetic confinement fusion and tokamak things, of which we are planning to simulate the sheath region. And then I will discuss briefly what we mean by plasma wall transition region, and then I will introduce the model and then a few results. And as I said earlier, if time permits, I will also show a few slides of the other activities, just introductory, or 1 or 2 slides to give you an idea what we are doing with other devices devices. So I'm sorry if I'm becoming very, I'm trying to repeat the very simple things, but I thought it would be better for those who are not involved in this field, especially students, to give an overview why we are selecting this problem. So as we know, nuclear fusion is the source of energy to our only star of our planet, the sun, and it has produced energy for us for billions of years. And unfortunately, it has already been tested for negative purposes like so-called hydrogen bomb, but we have heard it for many, many years. Now, what is going on with the commercial energy production or the energy production for household activities that can be from the nuclear fusion on Earth? Nuclear fission has been producing energy for so many years, but why nuclear fusion is taking so long? And this is one reason where plasma people are very strongly working. And although we are not directly working experimentally or involved in that field, so we just thought in our group that we could contribute at least to understand how it behaves in the world region. So as I said, there are many experiments and many researches going on. Now this is again a very simple slide prepared to give you or revise an idea what it means. And the main thing what we have to note here is when deuterium and tritium, there are many other candidates also for fusion, but deuterium tritium I will show in one of the slides to follow why deuterium tritium is preferred. Whenever we fuse them, it's not easy to fuse them, of course, because of the repulsive force between the positive charges. But if we could successfully create fusion of deuterium tritium, the energy gain that results is much higher by almost 2 orders. So this is one reason why people are trying to work on it. And to make it very simple, this is a very old slide, but still I like this one. What it shows is if we want to produce some energy, or if you produce energy by using 2 million tons of coal, same energy can be produced by roughly 1.3 million ton of oil like petrol, diesel, etc. But if the fusion starts working in future, we may need hardly 1 ton to give the same amount of energy. For a country like Nepal, we wish that India and other countries, they produce fusion as quickly as possible, because we are transporting everything. So we will save not only the fuel, the cost of the fuel, but also the amount of fuel that has to be transported. So this is one reason. But to make it more scientific, I have shown some of the slides here, which again say, if you want to run 1,000 megawatt power plant, and if you want to use coal, oil, and even uranium or fusion, this is the amount of fuel that you have to use. And you see the amount for fusion reaction to produce the same amount of energy is much, much less. This is one reason. And of course, there are many other, this is another work from Jülich in Germany. I just kept it original slide. This is what they say is the energy or the fuel required to produce energy for a household that need energy for 1 year. And this is just, the average, in terms of average, this is the average energy or average deuterium that is available in just 2 liters of water will provide energy sufficient for 1 year for a household family of the Germany standard. So in all these slides, what I'm trying to say is fusion is very, from this, of course, referred slides, what I can assure you is fusion, if it starts working, has the potential of energy. But why is it taking still so long? There is a movie here. I don't know if that would be interesting to all of you, but definitely for some of the students there, to motivate. It has sound, but it's not that important. So I'll just switch the sound off. Okay, so here in this clip, which was developed by a plasma lab in San Diego, what they are trying to convince or to show is to general people how nuclear fusion takes place and why it has been difficult, or why it needs so much of energy in the beginning to start fusion reaction. Of course, yes. Is anyone asking anything, or did I hear something? Okay, sorry to inform, there is no sound playing from this movie, so I'm just speaking on its behalf. The sound is not that important for us. So what I was trying
Nice session,
to
sir.
show
Nice
you.
session.
Yes, is there anything? Hello? Okay, maybe I'm just confused. Okay, so what? Okay, let me just repeat it once. What is trying to show in this movie is it is trying to explain to ordinary people, not to a physicist, not even to graduate students. When two positive charges come, why there is a Coulomb repulsion? This is just trying to show. But even if there is Coulomb repulsion, how fusion is possible? Because sometimes when we say the Coulomb repulsive force is very, very high, when we bring them together in order to fuse them, as R goes to 0, it will be impossible. But if we provide more and more energy, they come closer and closer. And in this picture, the two boys you wearing t-shirts, they are two positive charge. And the most important thing here is the mass defect which occurs during this reaction, this simple reaction of deuterium and tritium producing an helium nucleus and alpha neutron. It's so high that it shows in a very nice way graphically that in the San Diego Bay. Okay, I will let the picture roll and I will speak just in few seconds. Okay, what it says here is the amount of deuterium fuel that can be extracted from 1 inch of the bay that passes into the land from the ocean in San Diego region. The amount of deuterium can produce energy sufficient for 50 years to the whole state of San Diego. It is a relatively old video, but not many, a few years old, but still, this is very, very interesting thing that even though why we have not been able to produce fusion for so many years, even though it had so huge potential for energy, is this is okay, somebody is playing with the slides. Okay, if you want to explain something, it is okay, or I will just continue. So in this, what we see is whenever two positive charges come together, there is a problem in the beginning because we need to provide them sufficient energy so that they can start fusing. This is to inform that I'm not drawing these lines over here, the blue lines. Somebody is intentionally or by mistake using the annotation tool. So please excuse me if you are deviated or distracted. Okay, so what I'm trying to show in this slide is that whenever we have new fusion reaction between deuterium and tritium, of course, the fusion can occur even at low temperature, but the number of fusion for millions of particles, if it is very, very low, it will not become useful for energy production. So Lawson in 57 gave a very, very interesting criteria which clearly tells what should be the temperature and density and confinement time for any fusion reaction so that the fusion product can be useful, or the energy we are spending is less than the energy we will get afterwards. That means we will be having gain in the energy. And it shows that for various different possible candidates, like in this case, I have shown only 3. I have copied it from somewhere. Is in this figure, so if we have deuterium, tritium, and if you want to fuse deuterium, deuterium, or deuterium and helium-3, what we see from this graph, of course, please note that the temperature is in log scale. So this is 1,000,000 Kelvin. So you see the deuterium, tritium yields has the better efficiency even at low temperature compared to deuterium, helium, and deuterium, tritium. So this is why, because of the Lawson criteria, deuterium, tritium fusion is much more economically viable. This is one reason. And the second reason is deuterium is freely available, although in seawater, but although tritium may not be so that useful. But because of this, the temperature is so high. You see, this is millions of Kelvin. So I will show you very quickly in next slide. That temperature is a problem. not in the sense that it is not possible to raise anything at this temperature, but the problem is once we start confining any fuel in order to fuse them together, and we need to provide this much of energy, the temperature becomes so high, it becomes difficult to confine them for sufficiently long time. And here, the confinement time and density also play. Density is the number density, play very important role, because we want them to be as high as possible so that the Lawson criteria is over satisfied and we get more and more energy. And this temperature, if you compare this temperature with any possible temperature we know, what we see is, in this scale, just for information, I have shown that this is the absolute zero. This is somewhere we are in the room temperature. And then here is the temperature around which all the metals start melting. And this is the surface of the sun. This is core of the sun. But this is the temperature, which is even beyond the temperature of the core of the sun, is the temperature required to fuse hydrogen nuclei. That means deuterium and tritium fuse. So from this, what we see immediately is, if you want to heat something, of course, you cannot heat it in a conventional way. And if you want to create fusion, you have to heat it beyond even above the temperature, almost one order. This is nearly the same order, but this is 7 and this is 8 order of temperature. So beyond the temperature of core of the sun, obviously one question can arise, then how the fusion on the sun is possible even at low temperature? And that is because the sun has so massive gravity. The work that gravity does for the sun, we have to do it also by increasing the temperature. That's why on Earth, when we want to fuse something or when we want to start nuclear fusion, we have to heat it to very, very high temperatures. And this is where the plasma comes into role. That means whenever we start from any fuel, once we start heating them in order to create nuclear fusion, before the fusion starts, it reaches the plasma state. And once it reaches the plasma state, we need to continue heating it, and without letting it go away or disappear. So the problem becomes in fusion, always in plasma, in textbook or in research paper, if you look, there is people are worried about heating more than confinement. More about confinement than heating, because heating is not that big issue, because every time in fusion we are heating only a small amount of fuel. Now there are various mechanisms for confinement of such high temperature plasma. Of course, the best would be gravity. That has been demonstrated so far, but it requires huge mass like sun or the star, so we cannot do this on Earth. And the other two options are to use laser or high energetic particle, and to irradiate them and create fusion within their initial position. That means without letting them move from their inertial position. Now, in magnetic fusion, where I want to deviate today's presentation, is in magnetic fusion, what we basically do is, we know that charged particles, when they are applied by a magnetic field or when they are acted by magnetic field, they start gyrating, and they can be confined within, depending on the charged particle, their motion, the magnetic field can be varied so that they can be guided to a fixed region. So, and using this in magnetic fusion devices, the temperature can be achieved. And I have shown here just schematically, so far in fusion devices, the one they are doing experiments, they can confine plasma for a few seconds up to minutes, and their temperature, of course, should reach 10 to the power 8 Kelvin so that fusion can start, or the fusion can be useful according to Lawson criteria. And also the density is very less. So this is one of the area where people are working. And in magnetic confinement, there are very different types of confinement schemes, from Tokamak to Stellarator and linear devices and so on. Today, I want to concentrate more on Tokamak. And this is a picture I just wanted to show, that after this bad guy, Dr. Octopus in Spider-Man, he talked about, he got energy to fight. He became evil after he got energy, and the energy he got was from nuclear fusion. Although in the movie, it looked like he was a villain, but at least he gave some popularity in terms of, general popularity or interest of people in fusion energy. And this is a few years back, but still I remember this one. So what is basically a tokamak? Among many different magnetic methods or approaches where plasma is confined for the purpose of nuclear fusion, tokamak has been researched for many years, and it seems to be working fine and could be one of the first candidate to produce energy for commercial purposes. So tokamak is in fact a Russian acronym which simply means toroidal chamber with magnetic coil, and it has very strong large currents giving very strong magnetic field in the toroidal direction, which basically confines the plasma in a very, very small, if the magnetic field is very small, the Larmor radius will be small, and the magnetic field is primarily closing onto the torus. So the particle will just gyrate along, and in the process, it can be heated by various mechanisms like neutral beam injection, microwave heating, ohmic heating, etc., depending on temperature and the stage of the plasma heating. So this is one magnetic field that is responsible. But if you move a particle only in the circular orbit, there are many other effects that will try to disrupt the plasma out to the wall. Okay, it's not me, but if you want, you can ask me also in Hindi. I can. मुझे हिंदी थोड़ी थोड़ी आती है. Okay, so what we do in tokamak is there is a strong magnetic field in the toroidal direction that confines the particle, but in order to avoid the loss due to the motion in circular motion, there are other. This is just a cartoon of tokamak. Here you see the blue one. This also carries currents, and it produces magnetic field in poloidal direction, but very, very weak magnetic field, so that the field become twisted like spring, and the particle are guided in helical paths. Of course, they are gyrating along the trajectory, and they can be stable for relatively longer time. And just to give you an idea, this is a real picture in Princeton Plasma Physics Laboratory. Here is a guy sitting. So here, maybe not very clear, but you can have an idea. This is how these days tokamak research look like. And this is just one example, but I am particularly showing here all the tokamak research that are going on. And for me, every year, whenever our students try to go for excursion, the plasma students, they go to IPR, that is Institute for Plasma Research in Ahmedabad, Gandhinagar near Ahmedabad. And this is, they have a very recent so-called SST1 tokamak, conducting steady state tokamak. And they also have one older one, Aditya, which is, of course, as we all know, Aditya is the one, the sun god, our sun, our holy god sun, or the star sun. So they created sun on earth in Ahmedabad. And of course, there is one very close to us also in Kolkata. So what I'm trying to show in this picture is there are many different researches going on in tokamak. It is not that fusion has not been produced on earth, but all the researches so far could produce fusion only in the lab. And I'm trying to go to the point where we will be, when we will be getting fusion for commercial purposes outside the lab for good purposes, not for nuclear weapons. So if you look into this graph, just to compare the progress of fusion, which is represented by the blue curve, if you remember here, this axis on the Y is the so-called triple product. And here, this is the year. Triple product is, I'm sorry if I missed to say it earlier, but this is the indicator that fusion is very close to achieve this break-even, where it can be self-sustained and the energy can be produced without interruption. And it is the product of density, temperature, and confinement time. And here, this is the progress that has been made in many, many years. And here, just to compare with other experiments, like how, like with the Moore's law and with the energy doubling in the accelerators, very large accelerator, like Large Hadron Collider, we can see that the tokamak is progressing well. But of course, as long as it is not crossed this limit, we cannot say that it has achieved or the break-even condition that the fusion can be feasible. So the what I want to connect in this particular conference to people is there are many issues, and most of the issues are related with the materials, because the theory has been proved. It works well. The fusion energy is a real thing. Those who don't believe, they know how the hydrogen bomb or fusion weapon work. But the problem is, because we have a device which seals plasma, which is undergoing fusion at the temperature of 10 to the power 8 Kelvin. And after fusion, we are adding more energy into it, and we will have to derive the energy without letting the wall destroy. That means if the plasma don't reach the wall, we don't get energy outside. But if they reach in more, then we will not get the energy and we'll destroy the wall. So to understand this all, what I think personally, and of course this is true also, that we have to work hard in the materials, and of course also in the superconducting, thermally superconducting materials and superconducting magnets. So that's why this conference is very useful in order to discuss how the material should behave and what should be the nature of the material, and how can we increase the lifetime, or how can we estimate the amount of energy that the material is expected to receive whenever the fusion starts working. And that's why we wanted to work also in this area. So in terms of fusion reactors, you see what I said just now, sorry, I just moved 2 slides back again, is that the fusion reactor initially, they were very, very low in terms of fusion triple products, which is represented on the y-axis as the progress, very, very low. These are the earlier tokamaks. Now, with time, they improved so many phenomena that they could produce good results, but we have to reach here. So how we reach there, what is the next goal of the people working in this area? This is what I wanted to show here, is they are constructing a huge device compared to earlier or existing tokamak. This is a different scale tokamak. If you remember the earlier picture of Princeton, standing here, so it is like a huge building. Maybe most of you have already heard the name ITER. ITER stands for International Thermonuclear Experimental Reactor, but in Latin it simply means the way. That means it should show the way how the fusion community should move ahead in order to realize the energy production. And this is under construction in France and expected to produce energy in very soon. I'm not trying to connect it to some historical reason, but also sometime, it becomes easy to emphasize how hard people are working, or also the people earlier are working in this area. I remember particularly many prominent Indian plasma physicists, including Professor Kaur, Soda, Professor Srivastav, etc. You see, the concept of ITER started in 1985 when the two giants of that time, still they are giants, of course, they met and they wanted to do it, but the cost was so high, they didn't proceed further. But later, with the success of JET, with the European tokamak facilities, they decided to do it once again. And here, so far, this is considered as the most successful fusion experiments around, the first one, where they produced fusion power of the Q almost 2. That means they provided 10, the input power was 10 megawatt and the output power was almost 20 megawatt. And this is for a very brief time, although it was very huge success, because they demonstrated alpha particle heating. The plasma in the process. That means this is a huge step in the way forward to self-heating of the plasma. That means once we have plasma and we can start fusion, we can allow the plasma to self-heat so that the fusion reaction can sustain. And after this success, they came again together. And I wanted to put this slide because this is where we Nepali people feel proud that we are connected to IPR. And India is also a part of the ITER, who joined in 2006, and they have a very long agreement. And this money is just I got from the website from the ITER, and this is Nepalese rupees, by the way, which is a little cheaper than your rupees. So maybe, of course, you can get idea from this one. Usually in India, I hear you say itna 1,000 crore, but we say Arab. So it's like divide by 1.6 if you want to convert it to Indian. So what I wanted to show in this picture, this is a huge project. I mean, I think one of the most expensive scientific projects, but it is very, very interesting in the sense that the expenses are not to be paid in cash, in whatever I have understood. So it will develop plasma physics or research activities in all the countries they are involved. And of course, you can see most of the countries are involved because EU represents most of the European countries. And of course, because India is there, we also feel that we are also there. And it is expected that the fusion power, according to ITER, will be demonstrated something like in 2030 and so on. After that, maybe people in IPR who are representing India in ITER, they know it better, but this is the news that we can read in this website. So so far what I have said is fusion is, of course, proved to be has been proven to be a source of enormous amount of energy, and it has inherently less pollution in terms of radioactive waste. Of course, there are something, but which can be managed relatively easily compared to fission and other one. And it has the potential, and in terms of fuel, we have virtually inexhaustible. That means there are the fuel we have in seawater in terms of deuterium, tritium, or deuterium, basically, is so much that we cannot even think of using it. It's so huge deposit of fusion resources for fusion. And now still it has not been possible to demonstrate, but there are experiments and there are plans to demonstrate it by 2030, but that will be still an experimental reactor. And if you look into their site, what they are doing right now with the money that you have spent so much is this is an aerial view. This is not very old. I get from their website or the weekly newsletter that I get through my email. And now I'm trying to go into my problem, or the problem we are trying to connect ourselves to this very important topic. Maybe we are not doing so much. Recently, they started assembling of here. This is, I request you every time to look for something. For example, here is a guy standing. So we are like in an aeroplane or in a huge building looking at its bottom. And this is the part where the main tokamak should be located. And here, these are the cranes that are connecting or assembling these components that they receive from many different countries. As I said earlier, I'm not looking into this as a plasma physicist as a work of many different countries, but this is a work that should demonstrate how physics can be done at many different parts, and they can result in a huge project like ITER. It is not like, in my opinion, it is much different compared to LHC, because most of the components are not produced here, not in Europe. Some are in India, some are in China, in Japan, all the member countries wherever they get bidding or wherever they are allocated, and then they are transported here, connected. And in doing so, particular example of India, why I'm taking it repeatedly, we are benefiting. Every time we go to India, we hear something about ITER, and they are able to promote plasma activity or do at least something. And the FCIPT and other things, in my opinion, are the result of this one. So if you look into this figure, this tokamak site, it looks something like this recently, last week. So why I'm showing all this is, all the components that are coming from different parts. For example, here you see some people standing in just before they sent the cryostat part from India to ITER. This is not recent picture, but still this is from the Indian contribution. And there are some components being tested in Italy, some are in Japan, and some are in Korea. So why I'm showing all this, and I focus mainly in this part of the tokamak, that is so-called diverter. And I will now try to explain what diverter in a tokamak means. That is, and some of the components are produced in two places because they have to produce in a big amount. And in order to understand diverter, let me take you back to a result of G3D Tokamak that is in San Diego in USA. This is a cartoon picture, and this is how in one of the experiments they wanted to confine plasma, and they wanted to study how the disruption takes place once the energy is fed into it with time. And initially this D-Sept plasma that is here, this is the dotted line shows the magnetic field lines, and here two diverters on the two sides. Diverter are simply, in a tokamak, whenever we have a toroidal device to confine plasma, we can design it in such a way. The one type is called limiters, which try to limit the plasma as far as from the wall. But in diverter type, what they usually do is they have a specific point in the tokamak where they have specially designed magnetic field lines, which allows the particle to escape from those area in case it becomes more energetic, or this is the area where the particle hit the wall. So by doing this, what we are basically doing is the plasma never hits on any other parts except in the diverter region. So we know exactly where the plasma is coming, and we know how to design this device so that this can be replaced after certain sorts, so that this can, or the other rest of the plasma or rest of the machine have a better lifetime. So this is a picture, as I said earlier, how the plasma moves or how it behaves. So you see here, this is the plasma, and with the current variation and with the time, you see the plasma goes to this region. So what I was saying, referring earlier, is we can design a diverter region such that it can be replaced easily, relatively easily. Of course, this is not easy because this is a chamber and the plasma is deep inside. This is a paper. Now, this is one of the motivating factor for us to tackle the problem that we are doing. Let me see I already took a long time in these things. And this is one of the schematic diagram of how a diverter looks like. But for ITER, they are trying for many different options. But you see, this is a schematic picture. As of now, for ITER, they want to have a diverter type plasma. And here, I'm sorry for the very faint picture, but the red line shows so-called last closed flux surfaces. Of course, the magnetic field lines are everywhere inside, but in this picture, what we are focusing is in the magnetic field lines, along with the charged particle will gyrate and guided towards the wall in case of they run away from the core plasma. And this is the place where we have to focus more, and this is the reason where we have to extract energy, and we also have to protect the wall so that it becomes relatively strong. And the blow up picture shows that the red lines along which the particle will gyrate and follow towards the wall, they hit the wall at different angles. That means the obliqueness of the wall, magnetic field with respect to the wall is different. Some of the lines even look parallel to the wall. For example, if we consider a line very close to this green surface, if a particle gyrates there, of course, they will not gyrate with huge radius, but still, if they come gyrating, it may be scraped off by the wall. But if a particle, if you look into another one, they are at a slightly different angle. So this is one of the reasons why we want to simulate the plasma sheath. And in order to simulate it, we wanted to understand how the plasma behaves when they reach very close to the wall. This is a classic article by Stangway, also in his book, that this shows whenever the plasma particle face a material wall, depending on whether it's a heavy ion, whether they are propagating along the magnetic field line or at certain angle, they behave differently. And as they reach close to the wall, because of the magnetic field oblique to the wall, there is a so-called sheath and magnetic precede and precede. And of course, they are slightly different, but similar ones, and they have different scale lengths. And you can see that ion, electron, and of course, the scale length of these are very different, and the gradient over the sheath region is very strange. And whenever they reach the wall, because ion, electron, and the other particles, what I mean by other particle, if we have multi-component plasma, let's say some heliums are ionized, or some impurities are there, they will also reach to the wall at different with different physical mechanism. So in order to simulate this, we just wanted to understand this one. And we also wanted to understand how the imbining positive, negative, and positive and negative particles change the morphology, or how they interact with the surface. And to do this, what we did was we developed a so-called kinetic trajectory simulation model for a bounded plasma. In this picture, it's you just see, this is a drawing where we see that this is the direction of the plasma normal to the wall. Here is our wall, and the plasma comes from this side, and magnetic field is an oblique that makes an angle theta. Of course, in our simulation, we can vary the angle so that we can focus on what particular magnetic field line we are interested, or we can also see what will happen if the particle flow very close or very nearly parallel to the wall. Now, in our model, what we did was, of course, we considered all these phenomena, but we simulate only this region. As I said earlier, we are interested mainly in the Sept region. But whenever we want to simulate Sept region, we have to also take into account what is going in the pre-Sept region. That I will also discuss very soon. Now, the basic concept, what we do in kinetic simulation method in our case is we simply use the Boltzmann equation, or if it is collisionless. Of course, in most of our problem, we have discussed the collisionless problem. The reason is simply because in the Sept region, even when it is magnetized, only in the Sept entrance, that is when from the plasma side, very close to the region when they start leaving the plasma or start leaving the quasi-neutral plasma, they have gyration. Otherwise, close to the wall, because of the sharp gradient in the electric potential, they have very strong electric field. And because of this, there is no collision or less collision. And the second reason is Sept itself is so small, very often it is small compared to the mean-free collision path. So we consider collisionless. But in many cases, we have also considered collisional plasma. So we have been including also the collisional term. So what we do basically is we consider a distribution function from the injection side that is given from the pre-Sept region or from the core plasma. And once we know the distribution function, we move the trajectory forward in time. And we can move it forward and backward, and we draw the characteristics, and we see how the particle behaves. That means in this case, I just try to give an example. If we consider the particle to follow this type of distribution, we usually consider for both distribution cut off by the wall, and of course cut off because of the Bohm criterion that has to satisfy. This is sorry for this notation, but this is the step function that I want to show. And here for negative particles, we have, because of the negative potential usually that develops on the wall in order to maintain the flux or equality, or to contain the plasma stable, the negative wall has some cutoff to the electron velocity. And here we have considered the one-dimensional velocity towards the wall. And this cutoff in the ion velocity is due to the Bohm criteria. Otherwise, the Bohm criteria cannot be satisfied. And Bohm criteria, as we all know, in the basic thing that it has to be satisfied in order to plasma to be stable. Okay, now I will quickly go to this one. And this is our iteration scheme. That means initially we define the distribution function and the boundary condition. Of course, I should quickly, now because I lost so much time, I'm trying to quickly, hurry up, but I should not miss the general concept. So let me just give you once again the idea of KTS model, because this is the fundamental thing that we consider we have been doing is we solve the kinetic equation, but when we solve the kinetic equation, of course, we solve it self-consistently with all the Maxwell equations, whatever is necessary to, define our plasma, and the equation of motion, by satisfying all the property that a plasma should satisfy whenever the Sept is formed. And in this, whenever we want to move forward the trajectory, what we do is we solve the Poisson equation. So we specify the boundary condition. Usually the boundary condition we specify is the in the quasi-neutral region, we consider the electric field is very, very small, or in order to maintain the bomb velocity, we can calculate analytically the wall potential in some cases. So in other cases, we also try to incorporate the electric field and potential at the entrance or the point where we know. So once we have that, or once we know the initial, we provide initial guess to the potential profile, and then we solve electron and ion for the electron and ion distribution function. And for electrons, so far we have been doing it analytically by just slight modification by cutoff by the wall, because it's not necessary for the electron when the ions are moving to be considered by kinetic approach. And once we know the electron and ion density, we solve Poisson equation and we check for consistency or the convergence, and we know when we get the final result. So in the initial stage, what we did was we developed the model for simplest case, that means non-magnetic case. And with that result, for the non-magnetic case, we were still able to understand for the particle reaching to the wall, what will be the effect of particle emission. I mean, if the particle reaches with, huge particle having very large energy in the core, when they are detached towards the sheath region and they hit the wall, they may induce secondary electrons. I mean, in this, what you see is the particle induce electrons. That means whenever the particle reach the wall, if they induce secondary electrons, and if the ion can induce secondary electrons, how the potential at the wall is going to change. And if you look into this figure, it may not be very significant, just few volts, but it becomes very important, because we are trying to understand exactly how the wall is going to receive the particle and energy fluxes to the wall. And this is one of the earlier results that we could published using our KTS model. That's why I'm showing it, although it is not that very up to date, because it has no magnetic field, and it may not be useful for the case when the magnetic field is oblique. It is, of course, this result is still valid for the normal incidence or in absence of magnetic field. So this may not be useful for the fusion devices, but for other devices, this has received good response, that we could exactly calculate what is the energy and other parameters. How I can say just by showing potential that we can calculate other parameters is because we are doing kinetic simulation, and in kinetic simulation we can know the distribution function at every point in the simulation region. So once we know the distribution function, we all know that can be integrated for anything that we want to calculate, of course knowing the other relevant parameters. And this was our result was of course referred by others, and they also used calculation for by comparing with other results. So once that was done, why our result gave better, why our calculation gave better result in that case was, in electron density we did not just consider the Boltzmann distribution, but also we consider the cutoff by the wall. And this is our modification in the electron distribution, which resulted in the difference in density. And of course here we have normalized potential that has been plotted to compare with classic work by Besson. That you see, this is the work by Besson, and in our case, because of the electron emission, the potential shows similar qualitative behavior. But if you want to understand exactly what will be the value, so that if you want to calculate exactly what will be the property like energy or particle fluxes reaching to the wall, it provided better insight. This is just a comparison. Now, and the other thing what we wanted to do after we successfully demonstrated the 1D 1B single code was, the problem was with the coupling, because every time when we run our simulation, we are providing the input parameter ourselves. So we are in fact simulating only the sheath region very close to the wall, but we need to know what is going in the core plasma, and the core plasma parameter are usually the average parameter like temperature, density, etc. So that is dealt by the fluid codes. We know there is no necessary to discuss pre-sheath plasma using kinetic code because of the large scale length and very, very slow gradient of potential parameters, which you can see here in this figure in famous paper by Riemann. So what we decided is, how can we couple our code to core plasma, that means kinetic code to fluid plasma. So what we did was, we did it numerically. And for coupling, what we simply did was, of course, we know how density, temperature, and the other physical parameter are connected to distribution function. So we calculated using the our distribution function, we could calculate what will be the density at the sheath entrance. That is where the plasma starts moving towards the wall and where we expect the kinetic codes are much, much accurate. And this is the reason where the fluid starts. So at the boundary, what we simply assumed, it is very simple concept, that both the parameters, whether we calculate it by fluid approach or with the kinetic approach, if we are doing at the same point, it is something like if we want to know the temperature at Nepal-India border, at any point in when I'm crossing from here, let's say traveling to Ujjain through Gorakhpur, when I reach the border, if I go from Nepal side or India side, if we reach at the same border point, the temperature should be same. So similar, that simple concept are used to calculate the electron and ion parameters. And on one side, we have fluid parameter, on the other side, we have kinetic parameter that we obtain from our distribution function. We could solve this set of equation, at least numerically, to obtain sheath parameter or the kinetic parameters, starting with the fluid parameters. That means, every time, I will show in one of the slides below, that every time when we have a paper from any tokamak, because we are not doing experiments, we are very far away from experiments, but we want to connect it to fusion reaction. So when we get the parameter, we are usually getting the fluid parameters from the core plasma. This is our temperature, this is this. So what we did with this coupling scheme is we could manage, we could use this scheme and we could input the fluid parameter, and output is just the kinetic parameter at the boundary. And with that, we started solving for magnetized cases. Because of time limit, I will not go into every detail, but if there are any question, I'll be happy to answer. I will just now, because I want to give some time also for interaction. Just a moment. Oh, this is Nepali time. Okay, I have 15 minutes disadvantage. And here you see, once we have the coupling, we could calculate the flux of particle. You see, I'm sorry for the small symbol, but here you see the flux as well as the potential variation, how the potential changes for different temperature of the precise electrons. That means if we know the precise parameter, we can now reach up to the wall. This is an indirect way of connecting our result with the core, but we are connecting it numerically. And the good thing about this is, if there are any inconsistencies, we can modify our equation and we can run the code again. So in this work, in one of my PhD student, two of my PhD student with one of my colleague, we demonstrated that it is possible to connect precise sheath coupling, and they were compared with standard results, and they showed some consistency. And now, after that, we started including magnetic field effects. And what we had to do in order to include magnetic field was, of course, it looks very simple in equation, but in our code, we need to modify various things, because now we have to simulate or resolve velocity in all three components to consider the magnetic fields. And in addition to this, we also, of course, this is, and then once we have the magnetic field, we can, this is just the representative results for few angles, but in principle, we can do it for any result, because we are doing it only for sheath region, and we can input the theta parameter as any value. And this is the distance from the wall with respect to Debye length. And here we start somewhere in the core middle of the sheath from 5 to 10 Debye length. So we can practically look into any region wherever we have the differences, or where we want to calculate the exact values of this one. So this is a small result where we can see how the ion distribution changes. Of course, the ion distribution does not become linear with this angle, but because of the comparative scale with this one, it looks like this. But just trying to demonstrate it is possible. And then in 2014, we wanted to include the collision term, because in plasma, usually whenever we have, we are very close to fusion plasma, the electrons or ions that reaches into the sheath region, because some of them are even gyrating back, some of them are being cut off. So in collision has also to be taken into account. And in earlier case, we had constant collision term that we have recently modified. And then we could calculate also, this is a very important work in POP, where we calculate kinetic energy of ion reaching the wall for various magnetic field lines. Of course, most of our work, they seem to be of academic interest, but we try to connect it to the work of experiments. So in this work, what we try to calculate was what will be the various amount of energy or the flux of energy that every inch or every meter square or every centimeter square of the diverter which is facing the plasma is receiving, so that we know that what is the amount of energy that can be transported to the other side for the purpose of electricity generation, or what is the heat flux and other parameters, other physical parameters that can destroy the properties of the wall, so that we can warn, or we can be careful, or we can say when to stop the operation or when to change the parameter so that we can maintain the wall integrity. And this is also another important work. And this is a small piece of work that was locally published. And here, I just for the sake of completeness, I wanted to show that we also try to understand how the velocity varies with time. So this is still under work. It has to be published. I mean, not yet really great piece of work, but we have been successful recent times that we can also model, or we can also see how the velocity changes with time. And in this case, why we see like this is with time the particle moves towards the wall and the effect of magnetic field diminishes and the effect of electric field increases. So they stop gyrating as soon as they move away, and with time the electric field takes over. And today I wanted to present these results in more detail, but I will now go quickly into this. And what I'm showing in this paper, some of the recent work by one of my PhD student, is we try to focus. This is especially after we were in IPR in January and last year also, and in one PSSI conference, and we realized what we can do in order to contribute from the kinetic modeling to the real experiments of plasma is that we can try to tackle problems that are more practical. For example, whenever we talk about collision in the sheath region, or whenever we talk about the ion entering into the sheath, Mach number comes into role. And also the electron distribution is not always Maxwellian, and there are multi-temperature or temperature, electron having different temperature. And very often, because of the impurity and many other reasons, there is not only deuterium or tritium, but there are multi-component plasma. And also because of the magnetic field and the complex nature of electronegative as well as multi-component plasma, the Bohm criteria becomes modified, and how they interact with real surface. In this work, in the last piece, last one which I am showing here, I have shown example of carbon surface, but we can do it for any surface in our case. So we have done this for many surfaces. So what I am trying to show in this slide is that using our code, and of course we have demonstrated using some experimental parameters, that we could in fact, using our code, model various interests that could be of interest also for real experimental purposes. Maybe they may not give the exact experimental behavior, but what we can do is we can improve based on this, our calculation, so that we can get better results. So in order to do that, now what we did after that in our code is we took into account of exact particle gyration in perpendicular parallel direction, and we model this one. And of course, we, as I said earlier, we generalize the Bohm criteria, we modify the kinetic Bohm criteria for many different cases. The earlier Bohm criteria that we were using was for the simple, in the initial, it was for cold plasma, and then for some thermal distribution. And then now we do it for electronegative. Electronegative plasma simply means that if we have heavier ions, they are carrying some negative charge, so that they are not positive but negative charge as well in that cases also. And if there are multi-component plasma, we have a new Bohm criteria. So this was incorporated in our case, and of course this is a work that together with one of our colleague in India, in VIT, now he is in Delhi. that how the plasma wall transition and the wall sputtering. Now, in order to understand sputtering, now, as I said earlier, we want to make it as practical as possible. What we did with this, of course, with the support from Arun and his group is, we now use the coefficient or the energy that will sputter the surfaces. So we could finally incorporate also the effect of sputtering and energy that causes sputtering of the wall, and that effect, of course, not in the material properties, but in the plasma potential and other parameters. And as I said earlier, this is what we mean by the numerical value, or the parameters that we take as input is the parameter that we get from various experiments, and we get the fluid parameter, in which we use the coupling scheme and change them to kinetic parameters. And then we can, because we are doing a kinetic treatment following the distribution or the tracing the trajectory back in time where we know the distribution, we can calculate basically everything in our simulation region, like phase space, and the bomb velocity for different concentration of negative ions. Of course, usually the negative ions are not so high. They are very, very small in number. Usually the ions are positive charge, but if we have different concentration of negative ion, and we can also calculate what is the region where the electric force is dominant and where the magnetic force is dominant, and what sort of magnetic field variation or angle variation can cause in the changes in the parameters that affects the energy reaching to the wall. And this way we can control whenever, if we want to increase or decrease the energy fluxes, we can do that as well. For example, in this case, what you see is concentration of negative ions. You see the small number is simply because the negative ion concentration is usually very, very low in plasma, especially when they are coming out towards the wall. And with the concentration changes in concentration, we see how the potential profile changes. And as I said earlier, not only potential profile, but once we know the potential profile, we can also know everything else, because we are knowing the distribution function. This is just blow up picture of this one in the central part. And here the potential is positive because we have negative ion dominant plasma, and that's why the sheath. And this is just to show that in we can model, or we can obtain the distribution function in the parallel side as well as in the perpendicular side of the perpendicular with respect to magnetic field, of course. And this is at the injection point, and this is at the wall. This shows how the distribution function changes. The distribution function does not change significantly, but still we can calculate exactly by what parameter and by what value the area or the distribution function changes. And this is, of course, normalized with this with respect to the thermal velocity. And this is just three-dimensional impression of the same one for different type of distributions. Okay, and similarly, same results are continued in a different form that we can demonstrate. We can calculate ion density, electron density, negative ion density, positive ion density, etc. And okay, let me just go quickly, because I want to also show at least one or two slides of the other one. So I have said already, of course, I could not present most of the works in detail, but what we did so far in our work is we have developed a kinetic code. And this is a very simple code. Of course, initially one-dimensional, but slowly we have included three-dimensional velocity. And as of now, the most effective code that we have, the kinetic code, is 1D 3B code, but we are also including it. Some of our students are working in to make it 2D, or if possible 3D 3B. But so far 1D 3B is sufficient, because if you remember, the sheath region has a very sharp gradient of potential profile. So the electric field is so strong, the particle, except in the very close to the sheath entrance, they move directly towards the wall, or they are accelerated towards the wall. So most of the cases, the 1D approach is valid. But in order to incorporate the magnetic field, we should include three-dimensional in velocity. So we do 1D, 3D, and we modified the Bohm criteria, and we see that there is a change of about 1% in magnitude. Of course, this is not a large number, but if you want to understand the extent of heat energy carried by energetic particle, even a small fraction can be very, very important. So we could also model the effect of oblique magnetic field in all the properties of particle reaches to the wall, and we could control and understand why the charged particle, how the charged particle or the motion of charged particle can be controlled reaching to the wall. And of course, we included the effect of negative ions, temperature distribution, and we know that how the energy transferred can be calculated. And the ultimately we want to contribute in diverter wall modeling. And our aim, of course, it may look ambitious, but at least we want to contribute in the partial or integrated or complete tokamak modeling. But why we say that we want to contribute, even though we are just like beginner in this field and we are not doing experiment, is simply because if you look into ITER, this is just an experimental reactor, and once ITER starts working, it may take another couple of decades. I don't know exactly, because it depends on the result of ITER, but at least a few decades that the real reactor will start working. That means it may take up to 2050. So what I mean by the statement in this slide is, if we want to understand, or if we could understand at least how the diverter or the modeling gives some result in the diverter region, if we cannot use it in ITER, we can at least use in the other reactor that may come in the future. So this is all about the KTS model. I'm sorry I was not very appropriately timed. In the beginning, I spent too much time, and in the result part, I had to be quick. So I will not discuss so much in detail about this one, but I just want to show that we are not just modeling plasma wall transition phenomena in fusion devices. Of course, our prime goal initially was to model plasma that we produce locally, or our colleague in Kathmandu University, who one of our friend, Professor Subedi is presenting tomorrow, they are doing atmospheric plasma. So what we usually do in our TREAM effort is we model the plasma they want to generate, and they generate the plasma. So we were working that way. But in order to connect with the international community, we thought we should also go for fusion devices. So that I presented here today. And the second work we also do is we use a so-called Lie model code to simulate plasma focus device, which is a very small tabletop device that produces fusion in nanosecond, not for fusion, but for other purposes like neutron generation. These are some of the results in that work. And this one, which I said experimental work by one of my former PhD student in collaboration with one professor from India in Muzaffarpur, if you remember, Muzaffarpur area, and Patna, of course. What we did was we wanted to demonstrate that we can produce plasma also from local resources without buying sophisticated equipment. So what we did was we just used whatever we have available in our lab, and of course buying from the market, and we just demonstrated this way also plasma can be produced. And this is how I'm just showing it for some historical reason. Langmuir probe, how we made the probe, single and double probe, and this is our first plasma that look like this. And we have just used the line voltage, amplified line voltage, and rectified. It's about, and then in one of the work, what we did was we used the plasma generated by basic thing in collaboration with Subedi and one of my MSc student. When we treat a cloth, initially, of course, it depends on plasma, how we treat it or which type of cloth you treat. It becomes hydrophobic to hydrophilic, or the reverse is also possible. That has already been demonstrated. But in this case, what you see that initially, don't worry, this is not the blood, this is just the red color put in the watermark so that the photographically visibly it is clear. So before treatment, the plasma looks it is hydrophobic, they stay as a sphere, but after plasma treatment they absorb the cloth. So after we got motivated from this one, what we are now trying to do is we are producing plasma by very simple means. I'm saying it again because this could be our work. Every time when we present, it should be in a line that we are not very large lab, but we are a very small lab. In terms of computation also, we don't have big facilities, but we can still produce plasma, and we can still produce at least some work. Some people are interested, so that we could publish. So this could be a motivating thing for people mostly in the university who are not very into mainstream research. And these are our recent work of just before lockdown, shutdown. Now we are completely locked down. We are not allowed to go to our lab, not even to the lab. So you can, and what we are doing is we are producing so-called glided and other arc plasma. We have started using it for agricultural products, so that our work seems also to be related directly to our society. And we are using that product. Of course, it is not very stable yet, but when our plan is we produce atmospheric pressure plasma. Dr. Subedi will talk more about his work. This is an independent work, but still we are working in close collaboration with him. So what we are doing is we are looking into particular species of vegetables that are only available in Nepal, so that we are pioneer in that field in that way. And we want to treat them with plasma and see how it changes their growth, their longevity, and so on, maybe various other parameters. So finally, these are some of the references that were cited or were used in preparation. I'm sorry for taking a little longer, and thank you so much for patiently listening to me and for this opportunity. Thank you.
Thank you so much, sir, for this informative talk. And now it's time to take a question from the audience. The very first question is asked by Dr. R.P. Prajapati from Central University, Bilaspur. We want to ask that what is the efficiency of ITER and how it is better than jet Tokamak?
Okay. So I'm not into this field, but I'm very happy Prajapati ji is asking. And before I answer, I like to thank him for his very energetic contribution to plasma and contributing in conferences. And I'm not, if I say he was a student of Chhajlani sir, I'm sorry if I'm wrong. So Prajapati ji, I'm not into this field, but I can answer it easily because the ITER is not yet operating. It will operate in 25 and the expected Q value is 10. That means they will provide around 50 megawatt energy and produce about 500 megawatt energy. Of course, with your money, you are paying it. And the other thing is the amount of energy produced by Z was only 16 megawatt, of the order of 16 megawatt, and the Q value was just 1.6. So this is the difference. But of course, there are many different opinions by people that ITER will work or not, and so much money is wasted. For me, it is difficult to comment in that. But for me, it is easily possible to say that it will be a successful, because so much country, sometimes I make joke in Nepal. I'm sorry, this is not very good joke, but still, if it was we people, maybe we were wasting the money. But if it is so many Indian people, from Professor Kaur, I remember him very often, to recent people in India who are actively in this research field. If they are spending so much of money, they know it works. This is an indirect way, but the direct thing is the jet was working. That was an experimental reactor, and ITER will work, and the Q factor will be 10. I hope I answered your query. I'm sorry if I took long.
Thank you, sir.
Thank you so much, sir. Hope Prajapati sir got his answer. And the second question is from Narendra Purwalji. How Lawson criterion is fulfilled in the case of fusion device?
So it is maybe I'm not sure if it helps if I show the slide. In fusion devices, we should not be confused about the Lawson criteria, in a sense that it does not say about whether fusion takes place or not. Lawson criteria simply says, if the fusion takes place, will it be beneficial or not? This is the Lawson criteria. So what I'm trying to say is, even if you go below this temperature, the fusion may be occurring, but the frequency of fusion, if we input, let's say if we have 1 million of particle, maybe 1, 2, 10, 20 are undergoing fusion every second. But if we increase the energy, temperature, the number of fusion goes increasing. And this blue line or the blue border shows that if you want to produce fusion so that the Q value goes beyond 1, that means our output energy is more than input energy, we have to go above this blue line. And for that, in fusion devices, what they do is they configure the magnetic field such that they are contained for longer time. And if they are confined for longer time, you see the density increases and the temperature also increases. The temperature, confinement time also increases. And this is how they want to model or design the device so that they can increase both density and confinement time. Temperature, they don't want to play much, because temperature, it has to be 10 to the power 8 Kelvin, whether you use MCF or ICF, whatever. So in fusion devices, in magnetic field, they are increasing the confinement time and the density that can hold for longer time. This is how they want to use the Lawson criteria.
Thank you so much, sir.
But
few more questions are there.
Please.
Two more questions are there. The another one is, what is the influence oblique magnetic field?
Yes, it's a very interesting question, because imagine if we have a wall and if we have a normal magnetic field or no magnetic field, what will happen is the particle coming from the core plasma toward the wall, they gyrate like this and they reach to the wall. But as soon as plasma leave the particle leave the core plasma side, and the wall being very negatively biased in case of normal plasma, the electric field is very, very strong close to the wall, whereas very, very small close to the plasma. So as soon as we are away from the core plasma, the electric field starts dominating and plasma usually goes like this. So which I showed also in one of the picture from Stangbe. I will not go to that one for the sake of time. So what happens in oblique magnetic field, the particle go like this. So initially they are gyrating, they go like this. But in a normal magnetic field, if we had an oblique magnetic field, what will happen is the particle are coming like this. So the scraping off should also be taken into account by the wall. And what we have seen from here, it is not only our result, also it is consistent with other people's, they are working even experimentally and other approaches. What happens is, because of the change in obliqueness of the wall, the amount of particle reaching the wall at different time and the flux of energy reaching the wall changes. And usually, if the magnetic field is oblique, and it depends what temperature and density we are taking, it changes the property of the wall plasma or the energy reaching to the wall. When you are asking the next question, maybe I can go to a graph.
Yes, sir, sure.
So you can, no, you can just continue and.
Okay, the next question is from one of the MSc student of SSN Physics Ujjain. What is the best way to learn MATLAB and how it is run if anyone haven't licensed version of MATLAB? This is a very basic question.
So
every student want to know.
If you call me, I will answer differently. But in front of Swati madam and in front of Dean, I say there is no way. I'm sorry, but there is a way. And for me, it's a very, very tricky thing. My students now, they are using the recent MATLAB, which they get from internet. I will not talk about license. And I have a licensed version that is 2007. And it is licensed to only one computer, which I got it from my professor in Austria. And it is, that those days, it was not internet licensed. So it will never expire. And, my problem is sometimes when my students send me a MATLAB file, I cannot run into my MATLAB, but I do it in another laptop where I have, recent MATLAB, but I don't want to talk about license. You understood what I mean? And this is one thing. The best way of learning MATLAB is, now because I have to answer it a different question. So I'm thinking a very easy way. It is the same like learning a motorbike. You can ask somebody to tell you how to learn a motorbike, but if you want to learn to ride it, just ride it. But in the beginning, just ask them how to ride it, which is the accelerator. If it is a scooter, you don't have gears, the both are brakes. If it, I hope you know better how to ride a motorbike. If it is a scooter, both are brakes. If it is a motorbike, this one is not a brake, this one is brake, and this is accelerator, and so on. So what we can do is, if you want, I have given my email address in this. You can copy it and write me an email, and I will tell you. And nowadays it is very easy because we can chat hours and hours in Facebook or Messenger, WhatsApp, and I will tell you how is it easy. And the reason, maybe your question can be answered in a different way. When I was in the beginning, I had to model or I had to learn a computer programming. I tried many different programmings. I went to all classes, and why I learned MATLAB was it was window I could see. In Fortran, I learned that also, but I didn't use much. I had to write something, compile somewhere and write somewhere I could not understand in that time. But in MATLAB, if I write 4 + 3 and enter, it gave me result. So I think it is very easy to learn MATLAB, but it may take time to master it, but you will do it. It is just like a motorbike. For comparison. So I request you, and I'm very happy if you write me an email and we will discuss further. Also about license, I will tell you.
Thank you so
when
much,
it
sir.
is not
Definitely.
recording. When it is not recording.
Definitely, sir. Hopefully the student will contact you. So thank you so much, Professor Raju Khanal, sir. You started topic from very basic level and then you took it from to the higher, that is research and development level. It is simply amazing. As plasma is becoming center of attraction field of technology, so your informative talk not only help for those who are working on plasma, but also helpful to those who are just started their journey in research and development work. Thank you so much, sir. Once again, now without our audience, success of this event is not possible. Directly, indirectly, many hands are working. So for that, gratitude is must. So now I would like to call Dr. Nishchhal Yadav, sir, convener of EIPT-2020 for vote of thanks. Over to you, sir.
Am I audible? आवाज आ रही?
Yes, sir. Yes, sir. Yes, sir. Continue.
Okay, okay. It's my privilege to propose a vote of thanks on the occasion of the end of first session of first day of this international webinar EIPT 2020. With the sentiments of gratitude, let me extend a very heartful gratitude to patron of this event, Honorable Vice Chancellor Professor B.K. Sharma, who has been a constant source of inspiration for us. And on behalf of the organizing committee of EIPT and entire fraternity of physics and technology, and my own behalf, I extended a big thanks to the chairperson of 2 days international conference, Professor S.K. Ghosh, a renowned physicist and the former Vice Chancellor Vikram University Ujjain, for his graceful presence and guidance. And he has always been a source of inspirations to all of us. And I am also thankful to the chairperson of today's inaugural session, Professor Shubha Jain Madam, Dean, Faculty of Science, Vikram University Ujjain, for her precious work, precious words and elegant presence, and for the sparing some time in spite of her busy schedule. I would like to take this opportunity to thank our invited speakers, Professor Arup Niyogi sir, Professor R. Khanal sir, for accepting our invitations and for their excellent and the informative talk. Further, I would like to thank our H.O.D. Dr. Swati Dubey Madam for the perfect logistic support and the guidance she has extended to all of us. Well, an event like this cannot be happened overnight. In fact, the wheels start rolling weeks ago. We have been fortunate enough to have a team of very motivated and dedicated young faculties members of our department who knows their jobs and are result oriented. They are Ratna Agarwal, Priya Dubey, Dr. Priya Dubey, Dr. Ratna Agarwal, Dr. Apurva Mule, Dr. Kamal Jain, research scholar Subhash Chauhan, and the program which is conducted by Sai Shikha. I really thankful to the involvement and the willingness of all the students, participants, faculty members, and researchers who joined this webinar with a zeal of learning. Thank you all once again, and take care and be safe. Thank you all. Over to Saishika.
Thank you so much, sir. Thank you, sir, once again, and all the participants. Before ending the meeting, I would like to share brief highlights of tomorrow's session. Tomorrow will have three eminent speakers. Very first is Professor M. Jamil from Islamabad, Pakistan, Professor Deepak Prasad Subedi from Nepal, and Professor G.R. Sinha from Myanmar. Tomorrow, sharply at 9:30, our second session will start. So all of you are requested to join us on meeting well on time. Thank you so much, everyone. Have a good day.
Thank you all. Now I am ending this session. Shall we end, Subhash?
Yes.
Thank you very much once again.